And because it's after the the opening session, so a bit time has taken up from our side. We apologize for that. About Dr. Angela Samuels, the audience, I would like to say that she has been from National Metrology Institute, Australia, a renowned name in the field. Dr. Angela is an experienced director of international relations with a demonstrated history of working in the research industry. Skilled in international relations, research, international project management, proposal writing, and capacity building. Dr. Angela is a strong stakeholder management professional with a Doctor of Philosophy in Astronomy and Astrophysics from the Australian National University, Canberra. She is passionate about celebrating diversity, achieving equity, and ensuring inclusion. So her role is very helpful for the Metrology Society, in particular in the APMP region. And in fact, her today's talk will be about inclusive metrology culture among the APMP developing economies. So that's going to be very useful for us. And ma'am, this session is chaired by our Honorable Director, Professor Achanta Venugopal, and I am assisting him, Dr. VPS Savana from National Physical Laboratory. So ma'am, you can please start now.
Thank you very much. Okay. And I'm just trying to share my presentation, so just bear with me if you could for a moment. Okay, that's not the right presentation. One second.
So it's going to be 20 minutes talk plus 5 minutes discussion with the audience. Okay, ma'am. Okay. Okay, ma'am. Go ahead, please. Thank you.
Thank you. Let me just check if you are actually seeing the presentation. Can you tell me if you can see that?
Oh, yeah. We can see that, and you are very well audible as well. We can see the presentation, and ma'am, you are audible also. So you can continue.
Can I just check that you're seeing the right presentation, because I opened the wrong one accidentally. Is this the one that's the growing a sustainable and inclusive metrology culture? Is that right? I can't see.
It's the one, right. Inclusive metrology, APMP, and developing countries. Right.
Yeah. Okay. This is the one. All right. Good. Good. Thank you. So thank you very much, Mr. Chair, and I extend warm greetings from the National Measurement Institute Australia to all participants in this conference. Okay. I also would like to thank. Sorry.
Please click on the PPT slide.
Sorry.
Your screen, so we're able to see the participants in the one half and the one half of your.
Yeah, it's all right.
Is that okay? Sorry. Thank you. Let me change that to. No, sorry. 1 second. Having a bit of an issue here. Let me do it this way, if that's all right. Can you see it now?
Yes.
Okay. Excellent. So can I also thank the organisers of this conference for the invitation to participate in a very prestigious event, and I would like to take the opportunity to congratulate the National Physical Laboratory India on your 75th anniversary, as well as on the success of the ADMET conferences. I wanted to note that this presentation actually has a special significance for me, as I was privileged to be able to participate in person in your first ADMET event, which was in fact back in 1996. So I'm sorry, Dr. Singupta, but I think that revises the dates that you mentioned earlier. So that event in 1996 was in fact my first international conference after I commenced at NMIA. And at the time I was presenting on behalf of my then boss and someone very well known to the international metrology community, Dr. Barry Inglis, who was the then chair of the Asia Pacific Metrology Program, or APMP. So it is wonderful to come back now after more than 26 years of working with APMP and to share some of my perspectives of APMP's journey, in particular in supporting developing economies in the Asia Pacific. And I note my role at present as chair of APMP's Developing Economies Committee. So my presentation has a bit of a different focus to the rest of the conference program. My aim in this is to convey that as we all work together to advance measurement science and ensure the ongoing relevance and integrity of the international measurement system, we must also recognise and prioritise the inclusion and active empowerment of all voices, including those that are perhaps less visible. This is essential to the sustainability and relevance of all of our endeavours for our societies. Please let me know if the slides are moving forward, are they? Are they moving forward? Hello? Yes, okay. I see someone has said yes. Thank you very much for that. So as George Eliot stated in a couple of centuries ago, what do we live for if not to make life less difficult for each other? So while some of you I know are of course very familiar with APMP, I want to begin with the context of how the program began, especially for this audience, because NPLI played a pivotal role as the joint initiator of APMP together with the Commonwealth Science Council back in 1977. APMP has been as has been the key driver for global cooperation in metrology since the Meter Treaty was established in 1875, the creation of the APMP network reflected growing recognition of the importance of standardization and quality for trade and export markets. In defining the objectives of the program, even back then, the complex issue of collaboration between economies at different stages of economic development was seen as fundamental to the objectives of APMP, enhanced with the early opening of its membership beyond Commonwealth countries, demonstrating even then the value that APMP places on inclusion and broadening of benefits to all. The measures to build capabilities in those first 2 decades focused on support for measurement traceability through bi- and multilateral comparison programs, visits by experts to assess needs of developing economies, and attachments of staff to developed institutes. It was only by the end of this period in late 1999 that the mutual recognition arrangement under the International Committee for Weights and Measures, the CIPM-MRA, was established. And in fact, this was driven by the impetus from APMP, which at that time was seeking to put in place its own framework of mutual recognition to reduce technical barriers to trade, to support the recently formed Standards and Conformance Committee under the Regional Economic Forum, the Asia Pacific Economic Cooperation, or APEC. An explicit focus on the needs of APMP's developing members was the subject of discussion around this time, and the Developing Economies Committee was established in 2000. The work of the DEC over the past 2 decades has relied on the wealth of expertise in APMP's technical committees, as well as APMP's leadership and partners outside APMP to support, in particular, effective participation in the CIPM-MRA, technical capability building, and awareness raising with domestic stakeholders. Technical cooperation activities have also been led by APMP's developed members, such as Japan, Australia, India, China, Thailand, and of particular note, Korea, with a dedicated Global Metrology Academy established in 2013. As well, from the early days of the DEC to today, regional capacity building has significantly benefited from the support of PTB Germany, in particular through the multi-year MEDIA, or Metrology Enabling Developing Economies in Asia program, which is working in close partnership with the DEC since 2014. Having provided an overview of the APMP journey, let me now focus on the path that the DEC has been on since celebrating its 20th anniversary in 2020. In 2019, I began my term as DEC Chair with the overarching objective of ensuring that the DEC over the next few years would be on a trajectory of growth, learning from the lessons of our first 2 decades, and actively considering the needs of APMP's developing members in an environment of rapid technological and geopolitical change, as well as increasing challenges that extend across borders and across metrology disciplines. The resultant strategic plan, covering the period 2021 to 23, brings together views from across the membership to develop effective responses as well as drive the needed changes ourselves. As is increasingly recognised, healthy organisations grow by learning from, adapting for, listening to and empowering diverse voices. The APMP's vision, DEC's vision then, is for a sustainable and inclusive DEC that works collaboratively to benefit society across its agreed scope of activities. We are delivering on this vision by improving accountability, learning and operational excellence, raising awareness and empowering and developing capabilities of all of our members to address real needs that are aligned with national priorities. And here I note the references by NPL's Director, Dr. Achanta, to the need to bring global solutions to solve local problems. This is certainly at the heart of the DEC strategy as well. We have also articulated our values, strengths and purpose in delivering on this vision, importantly acknowledging that our diversity in development, knowledge, resources and values is our strength and opportunity. And we are very focused on ensuring that what we are developing and delivering for the region is very much aligned with national needs and national priorities. The implementation of this plan critically and deliberately depends on the following factors: empowerment of new voices, strengthening of confidence as well as capability, and thereby building an effective, inclusive and purpose-driven cohort of future DEC champions and leaders. So we are implementing this plan focused on 6 strategic priorities. The first 2 are intended to support our accountability and effectiveness through enhancing leadership and governance capabilities, growing that cohort of future leaders, and encouraging collaboration between developing members for mutual support, including through mentor-mentee relationships with members at similar levels of development. As well, we are putting systems in place to monitor and evaluate the impact and success of our work programs, also for continuous improvement. And as I go through these slides, I've highlighted the individuals that are leading the implementation of these the plans to deliver on these strategic priorities. As well as tools for measuring impact, we are developing mechanisms to increase collaboration through the creation of a knowledge management system platform. The pandemic has very much increased recognition of the opportunities presented through virtual engagement, and we are keen to ensure that our developing members no longer have to solely rely on in-person capacity building activities. APMP established its multidisciplinary focus groups in 2014. These cover the areas of climate change and clean air, clean water, energy efficiency, food safety and medical metrology, and the digital transformation focus group was launched at the beginning of this year. A DEC strategic priority is to increase the relevance of the work programs of these focus groups to our developing members, recognising their importance to effective engagement with national as well as regional stakeholders and to supporting the achievement of the Sustainable Development Goal priorities. Noting that these work programs have not been presented in any order of priority, I would highlight here that our commitment to leaving no one behind is demonstrated through our focus on the 2 strategic priorities of supporting our members who have not yet achieved published calibration and measurement capabilities through the CIPM MRA's key comparison database, as well as future proofing. So this is to support our developing economy and engage with advances in science and technology. So this refers to adaptation and alignment with the revised SI, as well as development of digital transformation as relevant to the needs of our developing members as well. While the strategic plan was endorsed just before the start of the pandemic, we, along of course with the broader metrology and all communities, have of course done our best to take forward initiatives over the past 2 years, albeit limited to virtual engagements. There have been barriers and obstacles for colleagues in our developing member economies, in particular, of course, due to the pandemic, and I take this opportunity to note the outstanding work of these and others in the DEC community, including key representatives from NPLI, in supporting this work, despite their individual and organisational circumstances. So what are we achieving, and how is this leading to the desired evolution of the DEC? I've noted here some examples of the current status of the work programs in each of the areas of strategic priority. So, for example, with respect to the leadership and management priority, we are growing that leadership cohort, and each of those tasks of those strategic priorities are being led by representatives from our developing member economies, which is actually growing their confidence and capabilities in driving these work programs. We are also creating that knowledge management system as the collaboration platform I mentioned previously, and developing tools to evaluate and measure impact and success, and ensure that we have the right systems in place as we go forward to provide a much more structured and coherent set of activities to support our developing members. Through our task force on focus groups, we are already increasing the developing member participation in those focus groups that I mentioned previously, in particular climate change and clean air, clean water and medical metrology. And the developing members are already working together with the chairs of those focus groups to help shape the work programs to increase their relevance to their economies. I'll jump to the CMC task force before going on to the future proofing task force. The CMC task force is starting to develop roadmaps, working with 5 member institutes who have not yet achieved CMCs, and our technical committee experts to develop capacity building in order to achieve CMCs in mass as the first discipline that we are focusing on. And in terms of future proofing and support with respect to advances in science and technology, this task force has already undertaken an impressive range of awareness raising webinars regarding the revised SI, and also in terms of digital transformation and digital calibration certificates. In fact, right now, there is a webinar taking place in parallel with this conference, focusing on the SI unit for electricity, the ampere. And very recently, this task force has also initiated an interest group on automation to support those needs in our developing member institutes. So with that, I trust that I have been able to convey a sense of the path that we in APMP and the DEC are on, and why the culture of our community, no less than the technical expertise and competence we deliver, is essential to the sustainability and relevance of our endeavours and our ability to support our societies. Thank you again.
I'm Gopal from NPL. So I have one question to you.
Of course.
Are there any specific areas where India can contribute more to the DEC framework?
I think so. The DEC, and I know Rena is in the audience. Rena is, and Dr. Yadav are representatives from NPLI to the DEC. There has already been support for the CMC task force work. I know that Rena is also directly involved in the future proofing task force. I mean, essentially NPLI is involved across the board, but we certainly welcome any new initiatives or ways in which we can work more closely with NPLI in any of these areas that I've mentioned, or others in which NPLI itself is focusing that I haven't covered.
So So thanks. So, for example, like the PTB SARC program, like are there any programs of the DEC where we can initiate and then?
Yes. Yes, that's an excellent suggestion. One of the things we are trying to do, which I touched on, is that mentor-mentee approach, and certainly across the APMP region, there are sub-regions. Of course, there's ASEAN, there's the Pacific Island Forum, and there's SARC. And where there are those existing sub-regional activities, you know, the DEC would very much like to seek the support, in the case of SARC, of course, of NPLI, in reaching out to and I guess partnering more closely with the SARC member countries to support them in these areas.
Thank you.
Thank you for the question.
I'm VPS Savannah from NPLI. I would like to ask one thing that about NPR and electrical, the parallel session which you told is going on. Right, some conference is going on even at now when you are talking to us. About this,
I'm really sorry, I'm having a bit of trouble hearing you.
NPR electrical, I would like to know about the NPR electrical, right?
Yeah, yeah.
Am I audible? So if I talk in this quantum metrology terms, right? The electrical current. So what type of cooperation between the APMP NMIs is going on at present, and where is NPLI in that scenario?
So there is a technical committee for electricity and magnetism under APMP, TCEM, and you have got a representative from NPLI involved in that. I'm just checking the website to tell you who that is. Yes, you probably do know Dr. Biswas and Dr. Awana are both listed as members. So that is one area where NPLI is already directly involved. And the other relevant activity, I would say, is the Energy Efficiency Focus Group, which my colleague at NMIA, Dr. Ilya Badovsky, is the chair of. So I'm not sure if you're already participating in that, but I would definitely encourage that.
Okay, so thank you.
Any other questions?
I have a very short comment.
Good to see you.
Good to see you.
I'm sorry I can't be there.
Yeah, well, we wish you were here. Just a very short comment about what you said about the genesis of the ADMET conferences. I mean, what I meant was, I mean, it was certainly a pleasure meeting you in 1996, but in those days, the conferences were not yet called ADMET. They were called NQGT, MMGT, and that's how it evolved gradually. And finally, the name ADMET got stuck 2001 onwards.
Right,
So
right. Thank you for that clarification.
But things have been, series has been going on since 1994, 96 onwards. Good to see you again.
Good to see you.
Any other questions? If not, thank you, Angela, once again for
thank you. Much appreciated.
We'll meet you in person here.
Yes, I hope so. And congratulations and good luck with the rest of your conference.
Thank you.
Now we move to the next lecture from Dr. A. Gupta ji, and it's sometimes good to introduce ourselves also, to celebrate ourselves. Actually, I was told in the morning that Professor A. Gupta, that Dr. Awana should not talk much about it. Sir, I will not take more than 2 minutes, but those 2 minutes are going to be precious. Please listen to it. It's a matter to celebrate NPL, and we should. Dr. Sen Gupta had his PhD in 1980 from Delhi University. His work was on traveling ionospheric disturbances using satellites. So even PhD itself was related to satellites and those studies. 79, he joined his Time and Standards Division of National Physical Laboratory. 2 minutes is 2 minutes. I have to stick to that. So please be patient. Superannuated from NPL in March 2015 as acting director, holding the position of outstanding scientist. So that's a matter to be celebrated, holding the position of as outstanding scientist. He was engaged in research on extremely accurate time synchronization using the Indian domestic satellite INSAT. This work has led to the INSAT time broadcast services, which has been widely used in India. It's a matter of pride for the country. In recent years, he has been mainly engaged with research and development of atomic frequency standards and a new generation of microwave synthesizers for atomic frequency standards. These ultra-precise atomic clocks are known as CGM fountains. People from PFR, ISC, and different corners of India and abroad have used to be coming to see our code, these experiments and all that. Presently, his former group at NPL is building one of the most accurate clocks ever, based on the single capped ion of ytterbium. That work is going on, and we are hopeful that it will be realized very soon. Dr. Sen Gupta is a fellow of National Academy of Sciences, fellow of Institute of Electronic IT India, president of Metrology of Society of India, and senior member of IEEE. Professor Sen Gupta was awarded the prestigious O.P. Bhasin Foundation Award for Science and Technology in year 2002 for outstanding contributions in the field of electronics and information technology. Today's talk will be on soil moisture using the precise measurements or realization of soil moisture using the GNSS this refractometry. And GNSS is Global Navigation Satellite Systems. So this was the introduction for Professor Sen Gupta, and we should get stimulated from this one. We need more people coming out of that discussion. Thank you very much. Sir, please continue.
Well, thank you very much. I think it's a great honor to be invited to deliver a talk here. And as I said, I mean, if I were there, I would probably encourage younger people to be asked to give invited talks, those who are actively doing cutting edge research. But today, I mean, it was just in the introduction, Dr. Avana said that most of my life I've been doing time and frequency, atomic clocks and so on. But today's talk is a deviation. I'm not going to talk about atomic clocks anymore, but this is something that I've started doing recently. So a very elementary talk. So those of you, and this is meant for the younger people, but those of you who are senior, kindly excuse me for the very simple contents of this talk. Satellite system reflectometry. Reflectometry or interferometry is what we use. My collaborators for this talk are this student, Razi, and Shraddha Vashisht, who's a professor at the North Cap University. So also the small group, we have almost no funds at all, and we're just trying to set up an experiment. So what is soil moisture? The liquid and vapor forms of water present in the pores of soil are called soil moisture. Your soil is wet or dry, and it's an important fundamental element that affects the Earth's surface, hydrology, groundwater recharge. It's, in short, it's a very important parameter, you know, because the farmer needs to know when to irrigate the soil and so on and so forth. So it's an extremely important parameter to measure on a long term. So how the soil moisture measure? The first method is in situ. Of course, you take a little bit of soil, it is moist, so you heat it up and let the water evaporate, weigh it once again, so you find out the amount of water present in the soil. But that's a tedious but very accurate method. You also have in situ probes that you can put into the soil, and by time domain reflectometry determine the amount of soil moisture. But these in situ techniques are limited in their applications because you can do them only rather infrequently and in sample in a few places. There are remote sensing methods of soil moisture determination using microwaves. One uses satellites collected by satellites measuring microwaves reflected or emitted by Earth's surface. There are, in fact, remote sensing satellites which measure the soil moisture on a routine basis. But the difficulty here is because the coverage is global, the resolution is very poor. You don't get, you know, very short resolution. You can get resolutions of the order of tens or hundreds of kilometers and so on. Now, that's what brings us to this topic today. We are all familiar with the Global Navigation Satellite System, or GNSS. You are all very familiar with GPS, which you have in your mobile phone. This is a system, a constellation of satellites that go around the Earth and give you a position. And the technique is rather very simple. You have a constellation of satellites going around the Earth, and you are one of the users sitting somewhere on the ground. You don't know what your position is. So if you can measure, if you can receive signals from these satellites and measure the code phase arrival, namely the time the signals emitted by the satellites to reach you, if you can measure this path thing, and then by solving a set of simultaneous equations, a lot of mathematics, we are not going to go into that, you can determine your unknown position in 3 dimensions and also retrieve the time. The caveat is that the atomic clocks which are present on the satellites must be precisely synchronized with each other. So this is something that we are all familiar with. We take it for granted today. Now, one of the problems of this global navigation satellite system used for determining positions is what is known as a multipath. So what is multipath? See, as a user, you are standing not in free space, you are standing next to the ground. You have a huge amount of ground, which is a partially reflecting surface. It's not perfectly conducting, it's a partially reflecting surface. The signal from the satellite not only reaches you directly, but it also reaches you after reflection from the Earth. It's not a perfect reflection, but a partial reflection. So, and also if you have some building or a tree nearby, the signal can get reflected off that. So these extra paths traveled by this signal from the satellite are actually a source of nuisance for the position determination. So it's an important source of error in positioning using GNSS. But what is a nuisance or a source of error for positioning is an opportunity for remote sensing, right? So that's what we're going to talk about. See, supposing you are a user and you're standing somewhere on ground and this ground has soil which is moist, then you use a satellite, a GNSS satellite, you receive the signal directly from the satellite, it comes to your antenna, then the signal, and it comes at a certain elevation angle theta, which varies with time. The signal also comes after reflection from the satellite. I've drawn these two rays parallel to each other, with this satellite is extremely far away. It's almost at infinity. It's about 40 to 50,000 kilometers away from you. So these two rays are parallel to each other. So now one thing you straight away recognize is that the time it takes for the direct signal to reach the antenna and after reflection, these two paths are not identical. There is a certain amount of path difference between the arrival of these two signals. And that path difference by simple geometry is given by B minus A. B is this distance, A is this distance, right? So when you have two signals, adding up here vectorially with a certain amount of path difference, they are actually adding with a certain amount of phase difference. And when you have a phase difference between the two components, you can either have constructive or destructive interference depending on the value of the phase, right? Now, what happens is these satellites are not stationary here. They're actually moving. The satellite rises over the horizon, goes around. So this satellite, actually starting from here, it's actually moving across the sky. Now, you notice as the satellite moves across the sky, this path difference, P minus A, it keeps changing with time. It's not constant. So this path difference keeps changing with time as the satellite travels across the sky. Now, as a result, there is constructive and destructive interference between these two components, the direct and the reflected signal, as the satellite moves across. So as a result, the signal that the antenna receives is not of constant power. It is waxing and waning, depending on the phase difference between the direct and the reflective rays. Now, you see, this ground is not a perfect reflector. Had it been a perfect reflector, in the destructive interference, the signal strength would have gone to 0, and constructive interference, the signal would have gone to double the original amplitude. Because this is partially reflecting, the amplitude of this interference pattern depends on the absolute value of the reflective, real component of the reflectivity. And also, there is a certain amount of phase difference because this reflectivity is a complex number. There is a certain amount of phase associated with it, which moves this interference pattern sideways depending on the reflectivity. Indeed, this has been observed, this is routinely observed when you receive signals from GPS satellites or global navigation system satellites. So this is a paper from 2010. So as the satellite, as the elevation angle changes, so does the signal power. You see clearly these interference patterns. Now, this interference pattern is sitting on a trend because the satellite signal, the distance to the satellite changes with time. You can retrend this and then fit a sine curve through this and using least square estimation, and you get you can fit an expression, a sine wave through this. And this sine wave has an amplitude and a phase term, and these two terms depend on the value of the soil moisture. This is the simple principle of the technique, right? Now, hence, the multipath signal phase can be determined from the sinusoidal data. Indeed, these authors in 2010 have shown, and indeed many other authors have shown, that you can clearly see a slight phase difference on days, a day before, during, and after a certain rain event. When it rains, the soil moisture changes. You can clearly see the phase change in this interference pattern. So in more recent times, these are experiments, these are results done from the global position in the American system, the GPS. In more recent times, in India, we have our own constellation Navic, and there's a group in Dehradun, they have done similar work. And this experiment is very simple. You have an antenna, which is sitting at a certain height, about 2 meters above the ground. You put it in an agricultural field, and then you, of course, have a soil moisture, an in situ meter by which you get your results. So you receive the signals using this antenna, and indeed you see these oscillating patterns. These are the interference patterns that one sees, and one can fit a sine curve through this, determine the phase of this signal. So all this has been published in the literature. In North Carolina University, we are still starting our experiment. We haven't started. We will do it in a short while. In the meanwhile, we thought we would try and analyze theoretically, try to understand the whole process, and try to explain the experimental results obtained by these gentlemen, right? Okay. So then what this group has done is they have carried out this experiment over a long period of time, over several months, and tried to determine the relationship between in situ soil moisture measured by that instrument that I showed you and the phase of that interference pattern. And indeed, they show a nice linear relationship, right? So that's this relationship. So they have drawn this curve. So now we said we'll try to understand this theoretically. And for that, we use basic principles. We start from the beginning. We do a theoretical simulation. We start with what is soil. Soil can be classified into various types depending on the texture. And the primary components, like the primary components in color, are red, blue, and green. The primary components of soil are sand, silt, and clay. And in general, the general soil that you see is a mixture of these three basic components. And the most common components are silt loam. This is what we assume. So most of the ground around is silt loam, somewhere around these percentages of sand, silt, and clay, right? So we assume for our theory this percentage, right? Now, when you have this soil, you have to determine the dielectric constant of the soil. The dielectric constant of the soil depends on the soil moisture, understandable, right? And many people in the literature, and it's this dielectric constant is a complex number because it's lossy, right? So a lot of results are available in the literature on models of dielectric constant of the soil as a function of soil moisture. We'll not go into a lot of details, but we just take this work way back in 1985. They have described a model for soil moisture, a real part and an imaginary part. The imaginary part responsible for the losses. And these are the formula for the real part and imaginary part. S and C are two parameters that you adjust for the composition of the soil. So we assume the silty loam, and we got the dielectric constant as a function of soil moisture, right? And by the way, this is done at the frequency of L band, 1.4 gigahertz, which is fortunately the frequency at which the GNSS signals operate. Now, then, having found out the dielectric constant, we must find out the expression for reflection coefficient. So when you have, very simple, if you have an interface between two media having dielectric constant epsilon 1 and epsilon 2, then you have reflections, and these are, then you define what are known as Fresnel reflection coefficients. These are, no great discovery. These are textbook formula. You can determine the reflection coefficient for horizontal polarization and vertical polarization, where theta is the angle of incidence. All you need are the complex dielectric constants between the two media. And it turns out that our GNSS signal are not linearly polarized, they are circularly polarized, right-hand circularly polarized, and you can get reflection coefficients for circular polarization also. RLR means the incident wave is right circularly polarized, L means the reflected output is left circularly polarized, and so on, right? But we need not just the reflection coefficient, we need the reflection and transmission coefficient also, because it's a partially reflecting, partially transmitting. So without going into much details, so these are the formulas. Please don't worry about these complex mathematics, but these are standard textbook things. But important thing is, provided you know the values of dielectric constants between the two media, you can find out the reflection and transmission coefficient. Very simple calculation. Now, after that, what we do is, we assume that you have air, that's where the satellite signal comes from, you have soil, but then this soil is not uniform in its dielectric constant or moisture content. On the surface is some value of moisture content, but as you go down deeper, the value of the soil moisture changes with time. There is a certain amount of gradient that, so that's why we cannot use one single reflection coefficient. So what we use is a multi-layer approximation. So in a multi-layer approximation, you assume that first there is an interface between air and this, and then you assume an interface between this layer and this layer, between this and this, and at each interface, you can define a value of partial reflection coefficient and a partial transmission coefficient. So what is transmitted gets partially reflected and partially transmitted. Like that, you keep going on. So we found out, we did a little bit of number crunching, and we found out that if you take about layers of 2 centimeters thick and go down to about 20 centimeters below the ground, it's sufficiently accurate. So the kind of profile for soil moisture that we assume are these. On a dry day, on the surface, it's very low soil moisture, but you go inside, goes, about 20 centimeters deep into the earth. Whether it's a dry day or a wet day, the moisture never changes. It settles down to a constant value of soil moisture. So on a very wet day on the surface, also it's about 0.4, down below it's about 0.5 and so on. So we searched the literature and we zeroed in on these kinds of moisture gradients, right? And having found this, you can find out the dielectric constants and hence find out the reflection coefficient. So we did that calculation and we computed the values of soil moisture, values of reflection coefficients for different values of surface soil moisture. This is for left circularly polarized, right circularly polarized. And this is the amplitude of the reflection coefficient. This is the phase of the reflection coefficient. This is what we need to do that interference calculation. Now, one more parameter that needs to be taken into account is you have an antenna sitting there, and this antenna has a certain amount of gain pattern as a function of look angle, right? The antenna is designed so as to efficiently receive signals in the positive elevation direction and not receive anything from the lower direction. So that antenna elevation pattern also has to be precisely worked out. And it's not a big problem. One can take an antenna, put it in an anechoic chamber and find out the elevation, the antenna gain profile. So this is the antenna gain profile. So finally, when you put all that, lo and behold, we found that our simulation also results in such nice kind of oscillating patterns, very similar to what we observed as what was observed experimentally. Sorry. Right. And also you notice that we have done these calculations for different values of soil moisture, 0.1, 0.2, 0.3, 0.4 on the surface, and you can clearly see the slight phase shifts, right? Now, then what we did was we plotted a graph between the soil moisture that was assumed in this calculation versus the phase shift, this phase shift, small phase shift, and we got a graph like this, right? And now please compare this graph with the graph that these gentlemen have got. For a 10% change in soil moisture, 10% is 0.1 in our terminology, in that other graph is 5.73 degrees. And what we observe in our theory is 56.5, that's about 5.65 per 0.1. So it's a very nice agreement between our theory and the experiment. And so it gives us a great amount of satisfaction in trying to do a very simple theoretical simulation and, and successfully finding out that it agrees with the experimental observation. So that's what there is in my talk. So in future, we are planning to do actual experiments ourselves. We are trying to do some kind of innovations in this, which perhaps I've already overshot my time. Right? In summary, we have described a simple method of measuring soil moisture using GNSS interferometry reflectometry, and we have shown recent experimental observations using our navigation constellation NAVIC, and we have done a detailed theory using multi-layer reflection from the ground, and shown good agreement with the experimental observations on. So this is a very simple technique for precisely measuring the soil moisture using something which is already existing. You don't have to spend money on launching satellites and so on and so forth. So thank you very much.
I have one question. Please. I see there are two oscillations. One is the short range and the long range. The one which you're fitting to the sinusoidal is a short range, but then you're also showing in the largest.
Oh, there, you mean a big trend?
No, if you're showing the oscillations, you have a very large angular spread covering, say, tens of degrees. And then when you're showing the fitting, sinusoidal fitting, it's only over, say, less than 1 degree.
Just
ऑडियंस में बोले ना तब तो बैक देंगे 3 नंबर भी
Right. So here you're showing 0.25 to 0.5 degree.
right.
Right. And you also have oscillation. You have data.
You mean these things?
No. This is what you're fitting. There is also a long range period which is there when you're seeing data for example here. So there's a long range period which is there in this data.
Oh, you mean this trend, this?
Yeah, there are oscillations in this, right?
Oh, no. I mean, see, this is a very noisy data. This is a very noisy data. I mean, basically, there is only one oscillation. I mean, rest is an artifact of noise.
Okay.
I mean, if that's the kind of thing that we're trying to do in our experiment. We're trying to see if we cannot increase the signal to noise enough that we'll have only a clean sinusoid and not have to deal with a lot of noise.
Right. So the fitting which you're doing is within a small region of this.
Right. For example, let me go to this one. Yeah.
So you have one long range period and one short range period.
Correct. So this long thing has to be detrended out. That is happening because as the satellite rises, the real range to the satellite also changes, right? And that increases the signal level. Right? So you have a long period.
Any other questions?
I have a very common curiosity that for the agricultural purpose, this you are measuring it. So either they are interested in a integrated soil moistures over a certain depth or a profile, or just the soil moisture on the surface.
I think as far as irrigation is concerned, as far as the farmer is concerned, for the kind of crop that one sowed, the surface moisture is of great importance, not what is there a meter below the earth. Because the roots of his crop will not go to 1 meter deep, right? So it will be more affected what is near the surface. So for him, the soil moisture near about 10 centimeters to the surface is what is important for him.
I would like to know that whether this reflectometer measures the soil moistures over a integrated soil moistures over a depth of 1 centimeter or something like that, or just.
Look, I just showed you in those simulation calculations, the soil moisture on the surface, it varied from 0.1 to 0.4, and that's how you got those phase changes. But down below at 20 centimeter soil moisture, there was no variation at all. So to answer your question, what these phase changes reflect are soil moisture near the surface, not at the top. Subhashish has a question.
The study you have done with the L-band studies.
Correct.
So same thing can be done with the S-band, but I think it has less sensitivity of the phase.
S-band is less sensitive. L-band, it fortunately so happens that it's very sensitive.
And second thing, sir, why like you placed your antenna in the rooftop.
Correct.
And then the reflected
Oh,
signal.
no. We have not placed it on the rooftop. We have placed it on the ground at a height of 2 meters from where the soil
Okay,
is.
then any local variation does not affect the reflected signal.
Right. I mean, there are, of course, interesting things to do if you have a green cover and so on and so forth. I think there was one question. I'm so sorry.
I would just like to know, like, you are measuring the soil moisture over a particular area, or does it cover a large range? And does it depend on other
Well,
things like pH variation of soil and things?
Well, to answer the first question, it covers the area where, which is the point of reflection of the signal, which is not huge, which is only about few tens of meters. That's all.
So that would give an idea of the local variation, but if you
Correct.
have to cover the large area, then
If you have to cover large area, you have to increase the height of your antenna, so you cover large area. And about the pH, etc., those are matters of details which we discuss offline. Oh, one more question.
What time of the day ideally these measurements are done?
Oh, it is the satellite signals are available throughout the day. So there is no preference given to the time of day. I mean, these observations happen any time of the day.
As you mentioned, that the moisture is actually a day dependent. During afternoon, it will be easily evaporated. So
Correct.
will it not make sense to do the measurements during night or anything?
No, well, in the night you will get a different value if you measure because see, one pass of a GPS satellite takes typically a few tens of minutes, right? About half an hour, let us say. So if you carry out an experiment for half an hour during the day, you will get certain value of soil moisture. If you do it at night, you will get a different value, right?
So another question, very general, since you are coming from the metrology background.
Right.
So this is, I see this problem as like, if you have a cows in a playground and you want to count them, one way is that you directly count them. Another is you count their legs and divide by 4. Okay, so this method is like, count the cows' legs, divide by 4, making little complicated, and the accuracy, actually you're going to actually calculate the moisture content. So are we not playing with the accuracy of the system, which actually will be used by the farmer? Uncertainty in this measurements will be much higher.
I absolutely agree with you. But then, I mean, that is not to say that I should not do a more precise theory. I mean, the idea of doing this entire exercise is to somehow innovate and find out a way in which I can get very clean experimental observations so I can make more precise measurements, right? You follow? I mean, that's the philosophy.
Thank you. Thank you, Dr. Sengupta, for not as simple as problem as you have put it. Even the air epsilon can be different depending it's coming.
Correct.
Right. So there's a lot of scope for improvement, and yeah, thank you. Next talk is by Dr. Dakhate.
Yes, so next talk is going to be again from an NPL scientist, Dr. Sriram Dakhate, S.R. Dakhate. Few words about him. Dr. Dakhate is working on advanced carbon-based materials, including bilateral sealing, carbon fiber polymer composites, graphite composites, carbon composites, carbon form CNT. So everything is carbon, and CNT based nano composites, graphene nanofibers, and all that. Okay, so he's the next carbon man from NPL after Professor Behel. He was trained by him for his PhD. He published more than 200 SCI reports and all that, and importantly 9 patents related to carbon technology, some 10 book chapters and all that. Interesting thing is this, that in early 90s there was no ACSIR in NPL. Only few students were given the opportunity to do PhD from NPL, and we were not more than around 10. Among them, some are here in NPL, like social. We have 3 programs: radio science, materials, and the metrology. Radio science, Dr. Now Mandal and SN Singh are there. Mandal was with Professor A.P. Mitra and SN Singh was with Dr. K.K. Mahajan. I was in superconductivity with Narlikar, and Dr. Behal was known for as a carbon man. So S.R. Dakhate was doing PhD with him, and we were registered in Delhi University. Same way Sushil was doing in the solar cells. So this was the batch of students in early 90s who were taken for some projects at that time. And from that batch. One of us is Dr. Esad Hakate, and we are hopeful from him to be the next carbon man from National Physical Laboratory. Dr. Esad.
Okay, Dr.
So please
Rana,
continue.
thank you very much for your nice introduction, and I would like to thank organizer for giving me opportunity to discuss about little bit about advanced materials work is going on in my division. And when we are talking about the advanced material or advanced metrology, so material come first, then advanced metrology, because whatever the instrument, whatever the things we are making, these made from the material. So materials also is important. Another part is materials metrology to one side project on advanced material and standard. So NPL being a member of this WAMAS, I have also the responsibility to propagate and discuss about the WAMAS activity and why WAMAS is important for materials metrology that I will discuss here. So regarding to the advanced materials division, there are three activities: photovoltaic materials and metrology, and photonics material and carbon material. And in this division, we are doing different types of work: R&D on material development, metrology in solar cell, and BNG development and standard testing. We are providing the testing and facilities in the area of graphite, carbon fiber composites, ceramics, thermal and mechanical property. Then our group is also working on the recycling of waste plastic, solar cell and agriculture waste. So first is about the solar cell metrology. That is NPL. Maybe NPL India is the I think fifth country in the world who is going to establish the primary standard in solar cell photovoltaic measurement, solar cell measurements. So this NPL is establishing this national primary standard facility with the help of PTV Germany. And the beauty of this facility is the if you see the uncertainty measurement here. So what we are going to do, this is the very fine is 0.03% for the solar cell size 20 mm or 20 mm and 0.6% for 156 to 156 EMF for solar cell. So if you compare, this is the actual setup we are going to establish, and this whole process is going to finish by March 2024. And after that, we will disseminate this facility to the solar industry as well as the country for solar cell calibration. So if you compare internationally, where we are going to be, India. So there are China, in the world there are only 4 laboratories at present have this primary standard for solar cell calibration. One is China, then USA, NERL, Japan, Germany, and with the help of Germany, PTB Germany, we are going to establishing this primary solar cell calibration facility in NPL, and this is the location facility. So this is about the main activity of our group in the area of metrology. Another thing in new materials, our group is working on the roll-to-roll printable flexible peroxide solar cell. So this is the printer. This is about A4 size paper. This is indigenously made in the laboratory, and at present we are able to print up to the 3 layers. But there are certain problems of a thermal evaporation system. We don't have that much big facility. So we are not going to make this printable solar cell up to the A4 size. But we cut this into the small 6 inch by 6 inch, so that we can easily metallize whatever the infrastructure available with NPL. And at present, we are not getting that much efficiency. But we are working on improving the efficiency, and we are targeting about up to the 15% efficiency in a flexible solar cell. So ultimately, what we are going to do, this is the setup. Our scientists are working on this. So we have to make the roll-to-roll printable flexible peroxide solar cell on plate. So another program is also we are providing the training on the solar cell in skill development programs. We have the all facility, and because again, whatever
models we are putting in the country in different part of the country, and India is having varying the weather here means one part to another part. So this parameter is very much important to study how the performance of the solar cell are going to increase or decrease. So these are the different parameter, and we are providing the training to the all means solar industry people. So another area is I am working in the area of carbon fiber. So carbon fiber is nothing but the fibers in the diameter in the range of 6 to 12 nanometer micron, but that contains 92% carbon, and if further that carbon content is increased to 99%, then we can say graphite fiber. And why carbon fiber important? If you compare now aluminum, steel, or even wood, because these all materials are going to finish after a certain time. So we have to see for advanced material, and one of this is the carbon fiber, and all over the world, a lot of work is going on in the area of carbon fiber. And this work is started from 1816, first time in the Japan, this carbon fiber industry is dominated by Japanese. And this work, carbon fiber innovation started from 1960, and still it is continuous. And they are having two type of precursors. One is polyacrylonitrile, and another is the pitch-based fiber. So lot of work is going on, but India, no efforts has been taken place. Till means we don't have any industry of the carbon fiber in the country. We have, and in future, maybe India having a huge demand of this carbon fiber. So in this direction, we have taken initiative to work on the carbon fiber, and that is based on the pitch-based carbon fiber. Because in the world, 90% market is dominated by the pan-based carbon fiber. So pan-based carbon fiber, one of the problem is the cost. Because of cost is more than 50%, and processing cost is 50%. So if we can reduce the cost of the precursor, then only we can able to produce the cheap carbon fibers. So, and the cheap carbon fiber majorly required for mostly our aerospace industry, and as well as automobile industry and the construction application, because we are trying to replace all these traditional materials by advanced materials, means carbon fiber and carbon fiber composite. So in this direction, we are working on the development of carbon fibers from pitch precursor. Again, pitch is the waste material from the steel industry, because in steel industry, coal is used to the reduction of the steel, iron oxide, and whatever the byproducts we are getting is the coal tar. So coal tar is used for different application, but again, that having a lot of carbon content, and from that we can convert this coal tar into coal tar pitch, and that pitch is the precursor for the production of the carbon fiber. So NPL is working on this to synthesize low-cost carbon fiber from isotopic. There are two types of pitches, isotopic and mesotopic. And at the moment we are working, and up to certain extent we got some achievement, which we are able to make the continuous carbon fiber in the NPL, and further process is going on. So one of the application of this carbon fiber, because in India is playing this archery games in the Olympics, and we are getting also most of the time some medals and all these things. But all these materials, whatever the archery they are imported. Nobody is making in India. So here, earlier they are used for wood and all other materials, but now people are using lightweight materials, that is some carbon fiber composites. So in this direction, we are working on this material development, means archery limbs for archery equipment. So this contains two parts on the middle part and two end parts made from the carbon fiber component, and this is the aluminum alloy. Okay, so this aluminum alloy is also making by some of the Indian MSME, and we are helping them to make the carbon fiber composites archery bow. So at present, it came to this state, and we have to again process further and provide further testing. So this is the commercial one, and this is made by NPL. So after this carbon and carbon fiber, there are different electrons of carbon, and one of them is carbon nanotubes. And this is discovered in 2004. After that, lot of work is going on in the carbon nanotube area because this material are very high tensile strength, high modulus, and high electrical conductivity and thermal stability also. But it is very difficult to realize these properties because these are tiny particles. It is very difficult to realize these properties in actual application, and it is a very challenging issue. So how we can use the carbon nanotube in the bulk application? So one of the way is to make this carbon nanotube paper to use in particular application. So NPL has developed this technology by using the multiple carbon nanotube. So these are just like a powder. Okay. So this powder again, the technology is depends on number of factors, but this technology again is a paper making techniques. We have to disperse this carbon nanotube at particular solvent as well as surfactant, and we will make the carbon nanotube paper without any adding any chemicals or any binders. So this technology is developed by NPL, and we have this first this technology we use as a flexible anode material for lithium-ion battery in the caption project. So after that, when we are making the bucky paper, it is again the isotropic. CNTs are randomly oriented. They are not aligned in one direction. So we will not get the mechanical property. So how we can achieve the mechanical property in this carbon nanotube or carbon nanotube material? So one way is that we have to make the fibers. We have to align the carbon nanotube in one particular direction. That's like the cotton fiber, cottons, and we are spinning cotton fiber and twisting, so we will get a thread so that have the strength. So similar phenomena we are considering here, and we are making the carbon nanotube here by chemical vapor deposition technique. So here this is again furnace, and here we are putting the catalyst and other raw material and form the aerogels. So that is the CNT aerogels that is suspended in the environment inside the chamber. And once after a particular time, they are coming, we are winding on the drum. So what we are getting a sheet of the carbon nanotube. And from the sheet of the carbon nanotube, we have to pull the CNT fibers, okay, and twist it. So we will get the fiber-like structure, just like a cotton thread. Just I'm showing next time. So if you see here, this is the sheet of the carbon nanotube. After that, we are pulling it, and this is just like a fiber, just like cotton fiber. And if you see how the CNT fibers are conducting, so without any addition, just this is the CNT fiber. We are used as a conducting cable for lighting the lamp. So that much conductivity that material having just like a copper. So in future, what we are going to do, we are trying to encapsulate this CNT fiber in the Kapton tape and insulator. So just like a wire that is used in many electrical applications, and that having almost very good conductivity. So there is no issue of the conductivity, and this having number of applications. One is in aerospace industry, because in airplane lot of cables are being used, and that is all copper material, copper based, and copper having higher density. If we can able to replace, so we can reduce the weight of the material in the Airbus or in and also the performance is also improved. So this, if you see, this type of cables are used in many applications in the aerospace industry, even in body armor application. Earlier also we have one project on the establishing facility of the body armor. And in that project also we are trying to make use of the carbon nanotube to make the waste plate, so lightweight waste plate, so that can be reduce the weight and improve the performance. Because at present there are two types of waste plate used in the body armor. That is one is USMWP polymer sheet, and another is the ceramic. So ceramic is a little bit heavyweight. So if we can reduce, we can incorporate carbon nanotube into some certain extent, so we can reduce the weight of the ceramic plate. So for a soldier, it is easy to handle and working. So these are the different applications. So we are also working on the hydrogen mission, that is hydrogen utilization. There are, as the Prime Minister of the country announced the hydrogen mission, and there are three parts: hydrogen generation, hydrogen utilization, and hydrogen storage. So our component is, again, we are working on the hydrogen utilization. So where we are using the hydrogen utilization to the means development, means to produce clean energy by polymer electrode membrane fuel cell. So in polymer electrode membrane fuel cell, it is a clean source of energy. But again, it is clean, but whatever more than 90% component in this fuel cell use that is made from the carbon materials. Even though it is a clean, but all the more than 90% component made from the carbon. So one is the bipolar plate, one is the gas diffusion layer. So gas diffusion layer is the carbon fiber, carbon fiber paper, and the bipolar plate is made from the graphite composite. And we are demonstrated this technology in Team CSRI by using this linear graphite bipolar plate as well as indigenous carbon paper. And now again, at present, we are working with different industries, and so different industries also shown for instance BHEL and another industry. So we are discussing with them so how to take up this technology in the market. So this is means again biopolymer based carbon material, that is activated carbon. So this activated carbon is made from the again biopolymers. So we have to convert these biopolymers into the fibers by electrospinning technique. And by electrospinning technique, we have to convert into the carbon nanofibers, and we have to activate them by different means treatment, and then we use as a material in supercapacitor application. So there are a lot of different carbon-based material nowadays used in the supercapacitor application, battery applications. So our group is also working on the thermoelectrics material. So, so to convert heat into the electricity. So at present, our group is working on different types of thermoelectric material in different temperature range: high temperature, mid temperature, and low temperature. So this is one of the example of the high temperature thermoelectric material. And this is the device also we made from this with the help of BRC. And again, that electrospinning, now people are scientific community is looking for the flexible thermoelectric devices. So in flexible thermoelectric devices, we have to take the nanofiber sheet, because nanofiber sheet is very thin and it is flexible. So it can be as a support for incorporating thermoelectrics material, and we can make the flexible thermoelectric devices. And it is also known in NPL. Our group is also working on the development of fluorescence material, that is means color shift Intel Go ink, that is based on the photoluminescence. So this project is sponsored by SPC, and we have developed this technology, and we have given the material to them, and that material is equivalent to what they are commercially using at present. But further progress is going on in this direction. And this is again indigenous bioluminescent security ink material for different types of adding security feature in different applications, not only the currency, but different documents also. And some of the scientists are working on different types of 2D materials, graphene, MOS2, WS2. So I don't want to go into detail. So another area is the climate change. If you see in the any general any R&D in material science, people are working in the area of environment. So in environment, as per the Paris Agreement, we have to reduce the temperature by 1.5 degrees centigrade. And India is also committed to reduce the temperature on the earth, so that people should not suffer. So this all, whatever the temperature raising, decreasing is created by the human. So one quote, our problems are man-made, therefore they may be solved by man. No problem of the human destiny is beyond human being. So whatever the problems we are talking about, the climate change, increasing temperature, rain and all these things that created due to the human activity. Now human has to solve this problem. So for this, a lot of work is going on to solve this problem, and particularly in the area of environment and all these things. So if you see here, different sources of means greenhouse gas emission. So maximum contribution is from the fossil fuel, and how we can replace fossil fuel and how we can reduce the carbon dioxide emission. It is the one great challenge in the direction. A lot of work is going on. And in India, if you see here, whatever the electricity we are generating, maximum we are using the fossil fuel, and more than 700 million tons of the coal we are using for generating 200 gigawatt of the power, and 1.1 gigawatt of CO2 we are releasing in the environment every year. So we are contributing 2.5% of the global greenhouse gas emission. Okay, so how this problem will be solved? So we have to see solved by alternate sources, that is renewable sources. And one of the one problem is in the environmental problem is that in the country this means agriculture stubble burning, forest waste burning, MSW, all these things we are burning in the environment and creating the greenhouse gas emission. Oh, I will just okay. So this on this aspect, NPL is also working on converting these different types of waste into biocoal, and that biocoal may be used in the thermal power plant as well as in the steel industry also. So this is the setup of this pilot plant we have in NPL, and these are the different types of biocoal for different type of waste material. So again, our group is also working on the waste plastic to convert into the tiles. Multi-layer plastic, single-use plastic, low density, high density. I don't want to go detail. And again, we are working on this, how to make, we are installing a lot of solar module. Then after some time, again, there is a lot of scrap is going to be generated. So how that can be recycled? So on that aspect, our group is working. So overall, whatever R&D we are doing in the world, not only me and not you, but all over the world. And maybe thousands of papers every day are publishing in the number of more than hundreds of journals. So the findings of this, that more than 70% of the research have tried and failed to reproduce another scientist experiment. Whatever you are publishing in the, okay. So more than half have failed to reproduce their own experiment also. So this is published in Nature 2016. So if research cannot be reproduced, it means research funds are wasted. Scientists and technical enrollees slow. So why I'm showing, and only 10% of published science articles are reproducible. So if we are putting $50 billion in the research funding, and only 10% are we are utilizing properly, reproducing the result, so 90% money we are wasting. So how to solve this problem? So again, metrology is again important here. Okay, so metrology is very much important for reproducing whatever we are doing. So quality infrastructure is important for doing the good R&D, good research. So WAMAS is important here. WAMAS in intercomparison play important role. Okay. So again, this WAMAS Versatile Project on Advanced Material and Standard. This is established in 1992 during the 8th meeting of G7 Leader Economic Summit. So that time they have finalized 18 program, different type of program for different aspects. But only WAMAS is existing and it is doing well. And now India is also part of this program. And there are 16 countries, and all these countries, why WAMAS is important? Because all these countries members are all NMI. So if members are NMI, they have the quality infrastructure and all these things. So to promote world trade, innovation, adaptation of advanced materials, international collaboration, and provide the technical basis, harmonization of measurement methods, leading practice. So this again, WAMAS is helping in the standardization, whatever R&D we are doing in the world. Just I'm sure. So I don't want to go. So these are the means whatever the project we are proposing, that is through the technical work area. So who can involve in this activity? Anyone with expertise and capability in the area of study can participate, and there is no any fee, because again here there is no funding in the WAMAS. We have to work ourselves with self-support. Okay. So participant can be from either WAMAS member or non-member region also. Participants fund their own involvement in the study. Test material for interlaboratory exercise and supply free of charge. We have to, whatever measurement we want to do, we have to supply the material to other laboratories on our own cost. And that WAMAS website listed study, all these things, and contact the project leader, PW chair, and so these are different things. I don't want to get, this is how the WAMAS is working, and at present, international chair and secretary is NPL UK, and NPL India is also a member of SC member. So I don't want to go. So just I am showing NPL India is. So we are working on this project, WAMAS TWT38, graphene oxide polyimide nanocomposites. So by different techniques, we want to establish some correlation between lengths and modulus measured by the installed testing machine by tensile strength and DMA. So for that, we are making different types of material in NPL by incorporating graphene oxide. And this material we are supplying to our other NMI, that is Mexico, to Brazil, and NPL UK. These are some results of India, and after that we are supplying this material to different NMIs to follow the comparison. Another program, this is competition strength of damage composites. This is the carbon fiber input polymer composites. So this with the help of one private industry from Bombay, and NPL is also the project leader. So this is also one of the program. Okay, I'm finishing. Okay, so NPL also take part in the intercomparison also. Means we can take part. Means we will not introduce our own projects, but we can take part in the different intercomparison study. So that one of such study that graphene related materials, NPL is participated to characterize CVD derived graphene by Raman spectroscopy. Okay, and this in this this project, 17 NMIs have taken part, and they have analyzed the data, and ultimately they have published in 2D material, international interlaboratory comparison of Raman spectroscopy and CVD grown graphene. So I don't want to go. This is the way actually they are saying sample and European. Yeah, two more speakers are waiting actually. I don't want to go. Speakers are waiting. Please. Yeah. Okay. Very good. So, not much time left. Sorry, we can ask the questions later. Okay. I think it was very lovely to talk. It's a recording. Okay. So let me introduce to the audience the next speaker with the permission from Honorable Chair. Director Gopal. Next speaker is Dr. Vishal Ramnath from University of South Africa. You will listen to him just now. Vishal Ramnath is originally from Natal in South Africa. The person is actually his Bachelor of Engineering and Master of Engineering with specialization in thermoflow from the University of Pretoria, South Africa. After obtaining his engineering degree, he moved to the as an R&D metrologist, focusing on heat transfer work with the main specialization in radiation thermometry. So what we will listen from him will be in relation to the radiation thermometry. And now he is with the CSIR, Council of Scientific and Industrial Research in Pretoria, South Africa, from 2002 to 2007. From 2013, he is a permanent academic staff at University of South Africa in Johannesburg. Over the years, he has produced some more than 20 authored or co-authored publications in the area of thermoflow as applied to energy-related studies and on Monte Carlo mathematical modeling. So let's welcome Dr. Vishal Ramnath to deliver his lecture. Am I audible, Dr. Vishal Ramnath, to you? Okay, so it will be a recording and we are all
good morning, colleagues. It's Mr. Ramnath. You are audible. To the chair of the session, should I do a live presentation 20 minutes. Are we okay for time?
Dr. Ramnath, we will actually welcome you as if you can be live.
I can be live. Okay. I'm going to share my screen.
Yeah, we can. It's very much seen. It's all right, and you are audible also, so you can continue.
Okay. Just give me a moment. I'm just going to share my screen.
Okay.
Just a moment. To share the entire desktop. Okay, to the facilitator of the session, can you confirm you can see my computer screen?
Yes, we can see you.
Okay, great. I will try and restrict it to about 20 minutes. All right. Good morning. I'm Vishal Ramnath. I'm in South Africa, and good afternoon to the colleagues in India. My topic for today is the application and evolution of the Monte Carlo method in metrology uncertainty problems. Little bit of context. I worked for about 10 years in the national labs, and I've got about 20 years of experience. I'm from South Africa. South Africa is part of AfriMets, and I work at UNISA, which is the University of South Africa. We have about 400,000 students all across the country and all across the world. There are various campuses, and we're Open Distance Learning Institute. This is me. Yes.
Could you please use F11 or F10 to make it full screen?
Say it again.
Could you make the present view full screen?
Full screen. Okay. All right, there we go. Okay, so without taking too much time, it is a multidisciplinary university. We do science, engineering, and technology. We have a supercomputer. My specific background for the context of this course is, this talk is, I was the national signatory for pyrometry. I worked for about 5 years in the high temperature division, and then I worked for about 5 years in pressure, vacuum, and flow. And I maintain the national standards, and I have some experience in uncertainty analysis. I'm mainly on the computational side, but I also do statistics as well. This is a brief sketch of the talk. I talk about where we're coming from in the past in the context of the GUM and the uncertainty analysis, where we are currently in terms of the current status as it pertains to uncertainty analysis. So my context in this talk is mainly on the scientific metrology side, mainly for metrologists at national labs that are maintaining their primary APEX standards and that are interested in participating in regional comparisons and international comparisons. Of course, the industrial metrology uncertainty is also quite important, but the focus is more on the advanced high-level SI scale realization, whether it is in the kilogram, whether it is in the Kelvin, whether it is in the Pascal. So I'm more interested in about how to use the Monte Carlo method for the very, very high accuracy analysis. And towards the end of the talk, I talk about the evolution. Where are metrologists going in the next 5 to 10 years as it pertains to the national standards with realizing the national CMCs? That is basically the gist of the topic. And this is the formal abstract, which I won't repeat, and you can read through in your own leisure. So here's the context. Where we are currently, of course, there was the GUM, the Guide to Uncertainty in Measurement. The GUM is basically an evolution of the Klein-McClintock method from the 1950s. So for people in industry, particularly in the engineering sector, Klein and McClintock in 1954 developed their original uncertainty analysis approach. And then around about the 1990s, the metrology community came together to refine the Kleiner-McClintock method and standardize the uncertainty analysis approach. And essentially the GUM from the 1995 is a modernization of the Kleiner-McClintock that incorporates nonlinear effects and correlation effects. So the details is not terribly important. The gist of it is that you have a measurement model, you work out the uncertainty coefficients, the sensitivity coefficients through partial derivatives, and then you work out the combined standard uncertainty. So if you're a metrologist in a national lab or a national metrology institute, this formula is essentially your bread and butter that you do in your day-to-day calibrations. And whether you're in electrical or mechanical or chemical, this is essentially where we are at the present state. After you work out your standard uncertainty, you work out the effective degrees of freedom, and then either using tables tables in Excel spreadsheets or lookup tables, you work out a coverage factor. So if you have a confidence interval of 95%, you would then work out a coverage factor. Usually it's about 1.97, 2.0 or thereabouts. But in principle, you can work it out for any confidence interval, 95%, 87%, whatever the case is. So this is essentially the recipe of where we are with the GUM. Now, that is the current status from 1995 to about 2008. And the context is fair enough. There's a recipe, there's a document from the BIPM on how to apply the GUM, and the key criteria on how to use it and when it would be valid and accurate is essentially boiling down to three key points. Point number one is that the nonlinearity should be fairly insignificant. In other words, if you have a nonlinear function in a higher dimensional space, in principle, you should linearize it in some local neighborhood. The second point is that the central limit theorem should apply. Essentially, that means in practical terms, you have a Gaussian distribution at the end of the day, a bell curve. If the curve is not a bell shape, or if it's not a student t distribution, you essentially have some major problems on your hand. And then the final criteria is that the Velk-Sutterford formula should be applicable. In other words, you should have a Gaussian distribution, and when you work out an expanded uncertainty, the expanded uncertainty will only be valid in a Gaussian distribution and where there's a symmetric distribution. Based on time, I will show you an example of where we have a non-Gaussian distribution. So this is essentially the three criteria. And then if we ask ourselves, if the recipe is so simple, why do we go through all this trouble and bother to do a Monte Carlo method? What is the point of a Monte Carlo method? Essentially, the point is that applying the GUM at a scientific metrology applications level can be non-trivial. There can be a lot of technical challenges, a lot of mathematical issues, and it is not necessarily as easy and as simple as people may perceive it to be. I'll give an example. I'm a mechanical engineer, and I will give a fluid mechanics example. We have a problem of the flow in a pipe. The pipe is a certain length, it is a certain diameter, and we would like to work out the friction factor. The friction factor is defined in terms of a nonlinear equation. This is the term that we would like to work out, F. F is defined in terms of an additional complicated function that incorporates F. So essentially, this is a nonlinear implicit function. There are various mathematical terms that I will not worry about. And the gist of it is that in practical engineering, physics, and chemistry problems, when we apply the fundamental laws of physics and chemistry, typically we will have some sort of complicated nonlinear equation, differential equation, integral equation, partial differential equation. And in only very special circumstances can we work out an analytical formula. Y is equal to f of x1, x2, and so on and so forth. So that is why we need a Monte Carlo technique, because we can't solve the problem and work out the sensitivity coefficients at the end of the day. When we incorporate even a simplified model, even the simplified model can be quite nonlinear. I'll give an example. No, that's fine. So moving on, when we do the calculations, the details is not important. The take-home message is that typically we'll have a complicated nonlinear function, and the GUM would essentially work out the uncertainty for a linearization of the higher dimensional problem. When we compare the uncertainty calculations with the nonlinear function and what the GUM would give us for the uncertainty, we will always have some errors. Regardless of whether we apply the GUM consistently, mathematically accurate, there will always be some sort of error. And that is essentially the gist of why we would like to work out a Monte Carlo method. I skipped the technical details and I move on to the gist of the underlying problem. So what is the underlying problem? From a statistical point of view, there is a mismatch of uncertainties between type A uncertainties and type B uncertainties. Without going into too much technical detail, the gist of it is that type A uncertainties are statistical uncertainties using frequency statistics. In other words, if you're a metrologist and you're working in an electrical lab and you measure a resistance and you take a certain amount of repeat measurements and you work out a standard deviation, that is a type A uncertainty. Why is it a challenge and why is there an issue with type A and type B uncertainties? Essentially, from a practical physical point of view, you can't take repeat measurements in every particular case. In certain scenarios, it's impossible to physically measure certain terms. And in those particular terms, situations, you make an assumption, an informed guess as to what the uncertainty is. A typical example would be you have a multimeter and you use a manufacturer's specification and it is a rectangular distribution and there's a tolerance of about 0.5%. So you take a rectangular distribution, you convert it to an equivalent Gaussian distribution, and you say, this is my best estimate of the standard uncertainty of my voltmeter. Whether you're using a voltmeter in a solar cell characterization or a time measurement or a satellite calibration, you make certain assumptions, and these assumptions assign a probability to what you think the uncertainty is. The problem is that the probability assignment uses Bayesian statistics, and the repeat experimental measurements uses frequency statistics. These are two different types of statistical analyses, and it causes a mismatch. Without going into the details, when you use the GUM analysis, you always end up with what's called an uncertainty of an uncertainty. Very briefly, if you take many repeat measurements and you work out a standard uncertainty, a standard deviation, you will always have an associated uncertainty in the variance. So you as a metrologist, I worked in pyrometry, I worked in pressure. If I do a physical calibration in the lab and it takes me 1 or 2 days and I do 30 repeat measurements, physical actual equipment measurements, I would work out an uncertainty for a particular measurement. Even if I had to do 100 different measurements, I could reduce the uncertainty, but there would always be an uncertainty of my standard deviation. And that is essentially why we have the Monte Carlo method. If we use a Bayesian statistics approach with the Monte Carlo method, in principle, there is no uncertainty. You could do a MATLAB program, an Excel spreadsheet, a Python program. If you assign PDFs to a measurement, in principle, there is no uncertainty. You can work it out to 10 or 20 decimal places. With a GUM, there is always an uncertainty of an uncertainty. So in simple terms, the GUM currently is using sensitivity coefficients for analytical models, and it is using Monte Carlo methods. In the next couple years, 5 years, 10 years, 15 years down the road, everything would be aligned to how the Monte Carlo method approach works. So in future, everybody would need to know how to do Monte Carlo simulations. So where we are in the past, nonlinearities, we could take higher order terms, central limit, the assumption of a Gaussian distribution, you can't do anything about it. The Welk-Sutherford formula, you can't really do anything about it. And this is essentially the recommendation as of 2022. Use the GUM for very simple models, and for more complicated analyses, for example, your primary standards and possibly your secondary standards, the recommendation is to just do a Monte Carlo. Simply avoid the limitations in the GUM framework and just work it out exactly with the Monte Carlo technique. So this is a picture of an early result by Professor Maurice Cox from the National Metrology Laboratory in the United Kingdom. And the early models incorporated various simulations and scatter plots and coverage regions. I give some references and you can look at it in your own time. In the mid 2000s, myself as well as various other colleagues, we extended it beyond the scatter plots. This is a scatter plot of a Monte Carlo simulation. The details is in the paper, and we constructed the actual bivariate joint PDF. In other words, the probability density function in higher dimensions. So we went away from doing scatter plots and histograms, and we plotted the actual distributions. This is the recipe of how the Monte Carlo approach looks like, which I will not talk about. And this is just of how to do it. You have a measurement model, you sample values, and you post-process the analysis, and you work out some distributions. To summarize where we are and where we're going to in the future, if you have a nonlinear model and there is non-Gaussian behavior, and if it is a single variable, you basically work out a quantile function using extended lambda distributions, and you determine various real numbers, A, B, C, D, and you fit it into a CDF, a cumulative distribution function. If you have multivariate models, 5 inputs, 10 inputs, 22 outputs, Y1, Y2, Y3, of any degree, you work out a covariance matrix. A covariance matrix is essentially a square matrix where the diagonal terms are the uncertainties of your output and the off-diagonal terms are the covariances. What happens when you have non-Gaussian behavior, where there isn't a simple bell-shaped curve, either in 1 dimension or 10 dimensions? How do you do that? The short answer is you use copolas. Copolas is a mathematical object to model non-Gaussian uncertainty information, and you use copolo as an instrument to couple all the different nonlinear effects. The details is maybe outside the scope of this talk. Where are we going in future with the uncertainty? Well, in principle, you could have very complicated partial differential equations. How do you apply the Monte Carlo method to a partial differential equation? The short answer is you model the problem using any computer software. COMSOL multiphysics, ANSYS multiphysics, Nastran, Adams, whatever the computer code is, whether you're an electrical engineer or mechanical engineer or chemical engineer. You draw the problem, you define your mathematical model, you discretize it, you perturb certain things that where you know there is certain uncertainties, your boundary conditions or your initial conditions. You make perturbations, you mesh it, you solve it, you work out the result. You perturb it again, you mesh it again, you solve it again. You take all of the outputs and then you plot the graph, either as a PDF or as a CDF. And that is essentially the gist of where we are and where we might be going in the next 5 years or 10 years. I'm wrapping up the presentation in the next few minutes. So I've given a historical overview, I've given the contemporary analysis, and where to now? Where are we going as metrologists in the next couple of years? It is possible that there could be non-Gaussian behavior in the models. The assumption of a Gaussian distribution, the assumption of a a bell-shaped curve in 1 dimension or 5 dimensions is a wish list. In real practical problems, it does not happen. They could be nonlinear behavior. How do we deal with non-Gaussian behavior? The short answer is we don't. At the present point in time, within the GUM, as in interlaboratory comparisons and key comparisons, there is an assumption that any laboratory measurement would be a Gaussian distribution. If there are 5 laboratories and we all do repeat measurements, even if the measurements are nonlinear, the only way at the present point in time to analyze and get CMCs is to assume and hope for the best that there is a Gaussian distribution. In future, as the models become more advanced, it won't work like that. How do we handle the non-Gaussian behavior? Well, with a single degree of freedom, we use lambda distributions, ELDs, with the equation I showed. And with higher order problems, we'd probably have to use cupolas. An analysis or an alternative going forward for metrologists at national labs is to simply forgo the parameterizations. We would ideally try to optimize certain parameters and use this to summarize. A possibility is to use kernel density estimates. In other words, to use big data, machine learning, neural networks to approximate the actual PDF without any parameters. So we have a computer, we have artificial intelligence, a neural network, a machine learning algorithm, and it analyzes and calculates the actual PDF without any parameters. That is a possibility in the far future, but perhaps not 2 years from now, but perhaps 20 years from now. Fair enough. So when we do the analysis, the old days of metrologists doing repeat measurements in the lab and doing an uncertainty budget in an Excel spreadsheet, unfortunately, as things become more advanced, as technology and society demand better accuracies, the days of doing simple Excel spreadsheets it might no longer be applicable. We would need to use more advanced computer languages, MATLAB, Python, Julia, and we'd probably need to use more computer codes. It could be closed codes like MATLAB. It could be open source codes like Python, Phoenix, OpenFOAM, FreeCAD. So regardless of whether you are in a national lab in a developed country or you're in a national lab in a developing country, the issue with commercial computer codes is that it is closed. You can't look at the computer code. And this becomes a problem with regards to the validation and verification of your uncertainties. So the evolution would be to use open source codes like Python and R, where you can look at the actual computer code and there isn't a technical barrier to metrology. So if you're from a developing country and you don't have $1 million to buy a very fancy, expensive piece of software, you can use open source software because open source software can essentially give you results to whatever desire you need. This is how we do high performance computing. Typically, we use C++ code or Python code, which is freely available. And this is probably the way of the future for metrologists, to use open source software and to do simulations. Also, as if you're working in a lab and you have a laptop, there's cloud computing, and there's possibility that in the next couple years, probably in the next 5 years, cloud computing and parallel computing will be deployed on the cloud. So there'll be no conceptual issue of my computer is not powerful enough to do the calculation. I'm sitting at home, I'm at a laptop, I have internet, I can write my Python code, I can transfer it onto the cloud, and I can solve it on the cloud. So if you're from a developing country where you do not have a lot of money, or if you're from a rich country, or if you're from working across many different countries, you can all collaborate on the cloud using cloud computing. And what would happen is that as the partial differential equations become more complicated, you would use software like Autodesk, Inventor, and you would solve the problem in virtual reality. And then you'd use a scripting language like Python to put in perturbations, and you would solve the problem in virtual reality for many, many different cases. and you'd repeat the analysis, and that would be how you'd use a Monte Carlo technique to work out the uncertainty. So to wrap up in the next 2 minutes, where we are, fair enough. What are the problems? What do metrologists need to talk about in terms of how to use the Monte Carlo method? What are the challenges? Well, the challenge is that the Excel spreadsheets would no longer be fit for purpose. The days of where there's some anomalous measurement, you just add in a root sum square for something that you don't know and you don't understand, unfortunately, that will no longer work. You would have to be able to understand the anomalies in terms of the mathematical model and incorporate it into your code to do a Monte Carlo. In other words, no black box, ad hoc root sum square terms. What else would you need to know? Well, the straightforward Monte Carlo method may no longer be sufficient. If you're working in a laboratory and you have certain insights, you would need to add that physical insight into how you calculate the uncertainty. The technique is called Markov chain Monte Carlo. It uses a method known as Metropolis Hastings. And then if you're a metrologist and you have some complicated nonlinear behavior, how do you compare the average if it's not a Gaussian curve or a bell curve? The short answer is nobody knows at this point in time. And this would be a research area for the next 5 to 10 years. And then at the end of the day, when you do an uncertainty and you have a piece of paper as a certificate, the old days of where you give an expected value, a table of the true value, the measured value, the error, and uncertainty and an expanded uncertainty, unfortunately, that would no longer work. You would either need to use parameters, many different parameters, or curves or surfaces. And that is where I pause. Thank you very much. That is the end of my presentation. And I'm now open to facilitate questions. Thank you.
Clarification, right? When you mention, I mean, when you brought in intercomparison into the as an example, so if there is a non-Gaussian or statistics, right? It means like we do not have enough sampling. Right? If we have unbiased sampling, we should have a Gaussian distribution. If right, so this will be a special case example, right?
No. So you can do simulation, and after the Monte Carlo simulation, you can still get a non-Gaussian. I'm just going to try and share the computer screen again. I won't be in presentation, so I'm just going to. Can you confirm you can see my computer screen?
Not yet. Yeah, it's coming up.
All right. So this is some Python code for the fluid mechanics problem. The details is not important. So the flat surface is what the GUM assumes there is. So there is some sort of curved surface, and you take a linearization, you would always have some sort of error. Fair enough. Now, when you do the simulation for the particular model, I'll show you now. The details is not important. It could be physics, it could be engineering. You don't need to worry about the details. Right. So this is the equation. This is what the GUM assumes. The GUM is the green curve. It makes certain simplifications. It will be Gaussian. I did 250,000 simulations with the Monte Carlo method, and that would be the uncertainty in red.
I think I understand what you're saying. So my question was more about if I thought like what you meant is not assuming a Gaussian in Monte Carlo, but if the statistic itself is non-Gaussian. Right? So that's what yes. What I was asking about. If the statistics is non-Gaussian, then it means the sampling is not sufficient. Right? So I understand that in the method, what you're explaining. Thank you.
Right, right. Thank you very much. To the facilitator, is there any questions in the chat?
We do not see
No.
anything online on the chat. No questions are there.
Right.
So, one last question from my side is, how do you propose to reduce the computational budget? Because the Monte Carlo is always intensive and dependent on your initial guess.
All right. You can reduce the computational effort using adaptive sampling. In other words, you can do 5,000 simulations, check what the results are, then do another 1,000, another 1,000, so on and so forth. So it's not actually necessary to do 250,000 samples. Using adaptive algorithms, you can probably drop it down to about 10,000 simulations. That is one way to reduce the effort. Another way is to take smarter choices of how to sample. So instead of sampling and hoping for the best, you have some sort of distribution and you take a representative spread of points. And then you can drop it down to about 70 to 80 simulations for engineering problems. So I know it sounds controversial, but for engineering problems, you do an answer simulation. It takes maybe 2 hours, 3 hours to get to grid convergence. You can repeat that 80 times, and you don't actually need to do 100,000 simulations. So the perception of doing 100,000, 1 million simulations, no, in real practical terms, you can drop it down to about 80 if you sample and you're smart about how you sample. I think that addresses the question. Sir, is there anything else?
No, that's it. So there are no more questions. Thank you once again for accepting our invitation.
Thank you, colleagues. All the best. I yield the floor to the convener.
Next talk is by Dr. Insek Yang from KISS Korea. Dr. Insek Yang, am I audible from National Physical Laboratory, India? Hello.
Yeah. Hi.
Hi. So it's good afternoon from NPL India, NPLI. Dr. Insek Yang from KISS Korea is there now, the next speaker. Myself, Dr. EPS Savana, co-chairing the session, and this session is chaired by our Honorable Director, Professor Achanta Venugopal. Let me briefly introduce the speaker to the audience here, online and offline both. Dr. Insek Yang received his PhD degree in physics from the University of Chicago, USA. He joined KISS Korea Research Institute of Standard and Science, that is called KRISS, in 2005. Since then, he has been working on thermometry, especially on the international temperature scale and thermodynamic temperature measurements. He was awarded the Young Metrologist Award by Asia Pacific Metrology Program APM in 2013. He is working on acoustic gas thermometry and spent 1 year at the National Physical Laboratory UK in 2017 as a guest scientist. He is a very renowned scientist in his field of acoustic gas thermometry. He has authored over 80 papers in several peer-reviewed journals. He has been on editorial board of Metrology since 2017 and was the chair of the technical committee on thermometry, APMT, from 2018 to 2021. So let's welcome Dr. Insek Yang from KISS Korea to deliver this lecture on resistive ratio thermometry today to us. Dr. Insek Yang, please. You are welcome to continue.
Thank you very much for kind instruction. Can you hear me, or can you see the screen?
Yeah, you are audible, and your sound is also seen.
Can you see the screen?
Yes, we can see your screen.
Okay, thank you. So thank you for the invitation. I am Insek Yang from KRISS. I will talk about calibration of resistance ratio bridges. So that's mostly resistance ratio measurement. I'm from KRISS, NMI of Korea. I'm a thermometry guy, and some may wonder why we need to talk about resistance measurement in thermometry. And you are looking at now the CCT service category in thermometry downloaded from BIPM. And you can see that the category 2.8.1 is bridge linearity. And error of bridge, and certainly linearity or non-linearity of bridge is important in temperature measurement, because SPRT measurement, it's a standard platinum resistance thermometer measurement in the temperature scale of 1990, ITS 90, uses the ratio of resistor to measure temperature. So you measure the ratio of your resistance of your thermometer to the resistance of reference thermometer at the triple point water, the reference temperature of SPRT thermometry. Then you take another ratio, resistance at certain temperature divided by resistance of standard resistor. So you take these two ratio and you take the ratio of the two ratio to do the temperature measurement. So let's assume that your first ratio measurement is higher than the true value by 2 ppm, and your second measurement of ratio is also higher by true value by 2 ppm, then this error cancels out because we take the ratio of ratio to for the temperature measurement. We normally only have to worry about nonlinear error in the resistance ratio bridges for the temperature measurement. And secondly, when you rely on the absolute measurement of the resistance, so you send your standard resistor to the electrical department in your institute, and the best uncertainty it normally comes with is about 0.2 ppm, and that's equivalent as 0.2 millik. And in the highest end resistance bridges, the claimed accuracy from the manufacturer is normally only 1/10 of the 0.2 ppm. So that's normally 20 microkelvin. So it's not really satisfactory to rely on the absolute resistance traceability of the standard. And because you normally use ratio of ratio, you can do actually a little much better. So that's where this resistance bridge calibrator comes in, and this is how it looks like. And this is basically 4 base resistors and 31 combinations made from network of the base resistors. So you can make 35 combinations, and you take the measurement of ratio of the RBC resistance and your standard resistor resistance. And by doing least square feet with the fitting parameter of the resistors of base resistor, you can find the errors within your measurements, how they deviate from self-consistently determined combinations of expected ratios. And these errors can be seen as the errors from your resistance ratio bridge. So this is how it works. So in this work, which is already published March this year from Mark Pan, so you can see this paper if you are interested. So basically, I calibrated 10 resistance ratio bridges used for the thermometry increase, and they are from basically 2 different manufacturers, and their range of measurable ratio are different. So depending on the bridges, the number of truly available combinations varies. And also some bridges in certain settings, it's very slow. So it gives out the value in every 20 seconds. And in some cases, they are quite fast, and the number comes out every 1.5 seconds. So the number of measurement to be used for averaging purpose are different. So this is a result from two ASL F18 bridges, and I show this first because one of the bridge we corrected the readings using certain error model based on the least square fitting, and in the other bridge we did not have to use any error model. So, and when we look at this data that I will show you in next few slides, we have to have in mind that the ratio 1 ppm is equivalent to 1 millik. This is quite common in thermometry when most of the SPRT use is 25.5 ohm at the triple point water, and we use 100 ohm standard resistor. So when I use this linear error model for this one particular bridge, I have about 32 ppb standard deviation, which is equivalent to 32 micro K. And for this another bridge where I did not have to use any error model, it was about 27 ppb error in the resistance ratio measurement from the bridge. And this is a little bit more higher end bridge, claimed to have better performance in ratio measurement. And this is the yellow highlighted one is the settings I use for this particular bridge. And actually the result of the uncertainty assessment depends on what kind of settings we use. So we need to use the particular setting we use for the thermometry. So we have to use the same settings for the uncertainty evaluation of the resistance bridge and the actual SPRT measurement. So we measured two F900 bridges, and you can see that the uncertainty or standard deviation of the fitted value to the measured value is about 10 ppb or 12 ppb when the correction was applied, or 19 ppb when no correction was applied. And this is highest end bridge for different manufacturer Isotech. And this particular bridge has two different mode, 125 millivolt mode that has lower uncertainty but narrower range, and 500 millivolt mode that has wider measurement range but a little bit higher uncertainty. So we tested two micro K bridges for two different modes. And for the higher accuracy mode or narrower range mode, we have 17 ppb uncertainty and 13 ppb uncertainty. And for wider range mode, we have about 64 ppb and 50 ppb uncertainty. So using this RBC, we were able to assess the uncertainty of the resistance bridge, which is normally the highest chain in the traceability consideration. And this one, F800 or F17, is a little bit low, middle end or lower end bridge, which is normally used for the measurement of secondary grade SPRT or measurements in calibration by comparison. And this one has normally a resolution of 1 ppb, but we did take many measurements for averaging. So it turns out that they have uncertainty or errors in the order of 1 ppb, or normally slightly smaller than that. So three of the bridges in this grade, they did not require any error model in assessing the residue of fitting. So they all have below 1 ppm uncertainty, and this particular one is less than half ppm uncertainty. And for this particular one, quite old one, it has uncorrelated error near 1 ppm, but when linear correction, first order correction model has been applied, the uncertainty was about half ppm. So applying error normally helps to reduce the uncertainty, but normally it's quite burdensome to keep track of all these error models that we used. So if we don't have to use any error model, it's better not to use them at all. And we try to monitor or measure the stability of the full base register inside the RBC unit, because we thought that the stability of the base register or any register combinations in RBC is required only within like 24 hours, 1 day, because normally one set of full assessment of breach takes about 1 day. We try to assess midterm, so tens of days stability of this resistance, and it turns out that it is stable within 70 ppb and with a standard deviation about 30 ppb. And these numbers are better than the accuracy of the claimed accuracy of these kind of F700, F70 breaches by at least one order of magnitude. So we thought that maybe we can use the RBC, so the base registers and combinations of those networks as a set of transfer registers to compare directly lower end bridges to best performing bridges. So in this usage, the RBC become a set of 65 transfer registers to compare two bridges. So this is the result of our direct comparison. Here, the reference bridge, the higher end bridge, is one of the Isotech micro-K bridge in 500 millivolt mode, because we need to have wide range of the measurement, because this particular unit of F700, F17 measures the ratio between 0 to 4. So we had to use that. And the result of the difference between the reference and the bridges under test is shown in red X symbol here. And we overlay the data we get from direct comparison to the measurement result we obtained earlier. So we can see that for all four measurements, the results are quite similar. So for the moderately performing bridges, we can use the RBC as a set of transfer standard to directly compare the bridge to the higher end best performing bridge. And another usage for this direct comparison is that we can find which error model works better for one particular bridge. So here in the left, you will see two comparisons. One, the red one from direct comparison, one from the RBC fitting when first order correction model was used. And you can see that especially from this green area where they fit, they are quite consistent. But on the right hand, you see that the result of the direct comparison and the RBC self-consistent fitting deviates, especially in the highest ratio area, because in this case, for the RBC measurement, we did not apply any correction model. So you can, especially for the highest ratio end, it deviates more than 1.8 ppm, and that's quite a lot. So from this comparison, we confirm that for this particular F700 unit, first order correction works better. And we can confirm that direct comparison works well when you expect from the uncertainty you expect from the breach is 0.1 ppm or larger. So this shows the summary of the assessment, uncertainty assessment for 10 breaches for 12 different configurations that Chris owns. In general, we can say that accuracies specified by the manufacturer were confirmed. And this is the last slide. But we can see that, okay, so it works well so far, but we need to worry about or think about these things. And the first thing is RBC is still a very good register. It looks like a standard register. It's not quite a standard register, but still it is very good register. But SPRT is a coil of thin platinum wire, and it's not so good register compared to the RBC or standard register. So sometimes what works for RBC might not work for the SPRT. So your bridge may work very well when you measure RBC against standard register, but it's not really guaranteed that it will work as good when you measure SPRT against the standard register. So that's one thing we need to worry about. And also, this calibration of bridge gives the result in the standard condition, so most popular settings. But what about some, often we have to measure high temperature SPRT where the nominal resistance is 2.5 ohm or 1.25 ohm. And we have to use 1 ohm or 10 ohm standard resistor. So because these nominal values are changed, the settings should be changed. So can we use the result of the previous calibration to these settings? Probably not, and we need to find out how much we have to increase the uncertainty. And in some cases, in very low temperature limit, we still use 100 ohm standard resistor, but the SPRT resistance, particularly at the equilibrium hydrogen temperature, it's about 0.03 ohm. So around this value ratio, there's no conformable point, measurement point around this area. So can we still believe the measurement in this area where no neighboring confirmation was available? So this was open questions that we have now. Thank you very much for your attention.
Question? I have one question.
Yeah.
I mean, it's a very naive question. If you have a variable resistance bridge, when you are changing from one set to another set or one value to another value, how do you take care of the contact resistances and all? Like, so still retaining your PPB level of uncertainties.
Oh yeah, I don't know the details of electrical connection inside the RBC, but that's the core assumption of this unit. So in the manual, so I'm not electrical guy. So in the manual, it says because of the special technology that they use inside the register unit, even when we change the networks of the connection, it will maintain. So it will have the theoretical mathematical value. So that's like Harmon type connection. I don't know it quite well, but that's as far as I know.
Thank you. And there's one question.
Thank you, sir, for touching upon a very important problem. So you have not considered any DC bridge for the studies. And the second question is how much important this for estimating thermodynamic temperature and say T minus T90? Your insight.
For the second question, so obviously for T minus T90, we have to measure T90 very well. This is one of the, like, it's not big uncertainty component, but normally this is very difficult to measure. So normally we assume some nominal value from the specification provided by the manufacturer. So in order to reduce the uncertainty, or in order to make sure that you do the right measurement for T90, we have to assess the uncertainty of the bridge. So I think that's because of that, I think this is still important for T90 measurement, but also T minus T90 measurement. But I didn't catch the first question, so could you repeat the first one again? The first question.
Yeah. So you have not considered a DC bridge for your studies.
DC.
Yeah.
Oh yeah. So for this one, this RBC is supposed to work for both AC and DC. So you can see that two of the thermometer isotech, that's, as far as I know, that's DC bridge. Of course, you alternate the polarity of the connection within the bridge, but basically, I think we can say that's DC bridge. So it should work for both AC and DC.
I think there is one more question from Professor Ramanathan.
Yeah.
Greetings, Doctor. I've got two quick questions, if you don't mind. Question one, what is the time taken to do the resistance measurements for a bridge? So I'm from a temperature background. We do thermophysical properties. Can you use an RBC, and does it take 10 seconds or 10 minutes to do the resistance ratio measurement? What is the response time for the RBC?
So RBC is just a physical register, same as the standard register. That's the bridge that has the response time. So for different settings, it will give a different response time. For from these settings that I use, which I also use for the usual measurement, F900 20 second, F18 10 second, F700 1 second, micro K 1.5 second. So yes, and then I have this from 20 to 300 repeated measurement. So normally you finish the measurement of evaluation of one bridge per 1 day. I hope that answers your question.
Yeah, so you can't use an RBC for in situ where there's a transient response in temperature. Okay. My second question, on slide number 2, when you take the ratio of resistances, the water triple point, and of course the other thermodynamic points, when you take the ratio of resistances, the X value, in your uncertainty budget, do you incorporate the covariances, or do you disregard the covariances? You mentioned a low order error model and a high order error model. When you work out XTPW and XT, do you work out the covariances between those ratios?
Covariance from the errors in the bridge?
Yes. The covariances between the resistances. So covariance between COV open bracket RTPW comma R underscore S, the covariance between the different resistances. So you want the uncertainty in X, and then the uncertainty in X depends on the uncertainty on the numerator, and it depends on the uncertainty in the denominator.
Yes. that's so when we look at RS, our RS has the, for example, calibration uncertainty, but that calibration uncertainty, when the measurement is done within a few days, we can say that it completely cancels out, because assuming that your calibration of standard register is biased in some way, it will be still biased. It will be biased both in XTW, TPW measurement, in XT measurement. So that should cancel out. So we ignore that. But when the temperature of the standard register changes, it sort of changes randomly within some temperature interval. So we need to take care of the uncertainty due to the temperature difference when RS is used for at the triple point of water and RS is used at the temperature T. For that, we have to include in the uncertainty. But do we do that with a covariance measurement and mathematically correct way? Practically, I don't think we do. We just rely on simpler mathematical expression that, okay, this part of uncertainty we ignore. This part of uncertainty, okay, we take care of it. We do it more simply, maybe mathematically not so sophisticated manner.
That's perfectly fine.
Yeah,
and the ambient specifications of your bridge measurement, is it 0.5 temperature plus minus 0.5 and 10% relative humidity? What's the tolerance for the ambient conditions in your final results at the end of the day?
If I understand it correctly, because both of the RBC and the standard register is located in the oil bath, normally the ambient temperature does not give any difference. So it's quite insensitive to the ambient temperature or humidity.
No, the RBC is sitting on a table in the lab.
No, RBC, this is actually, even in this picture, it's actually inside the oil bath.
Okay.
Yeah.
Thank you very much, Doctor.
Thank you.
Thank you.
Thank you.
Thank you, Vincent. I'd like to close this session and thank all the speakers and Dr. Avana. Thank you.
Thank you.
So I thank Director Sir and Dr. Avana for chairing the session. It is my pleasure to share with you all that today is Dr. Dhakate's birthday also. So let us all convey him our best. Now I request Director Sir to felicitate Dr. Dhakate with a token of momentum.
कैमरा इधर कर दीजिए।
I request Sir to felicitate Dr. B.S. Avana with a memento. Thank you, sir. Because of shortage of time, we will continue for next session. This session will be chaired by Dr. Pawan Kumar Kankar and Dr. Nahar Singh. And Dr. Nahar Singh will co-chair the session.
जी जी तुम्हारी अरे बिल्कुल चिंता मत करिए साहब, हैं? हाँ बिल्कुल।
Dr. Pawan Kumar Kankar is Associate Professor in the Department of Mechanical Engineering, Indian Institute of Technology, Indore.
उधर रख देना बॉक्स में।
Dr. Nahar Singh is Senior Principal
नहीं बॉक्स है ना, बॉक्स में
ये देंगे, आपने बोला यहाँ रखवाने के लिए बोला है।
Indian Reference
उठा ले जाएगा बस,
ले जाने में यहीं बैठा हूँ ना।
चलो तो पहले नमस्कार डॉक्टर साहब। चल रहा है ना? हाँ सर, नोट कराना है। हाँ बिल्कुल, ये अभिषेक जी। ये सर का उधर फिजिकल प्रेजेंटेशन है, सर भी कर दीजिए। हाँ, एक मिनट इधर देख लो। ये अभिषेक सर का पहले इधर कर दीजिए एक बार, सर जरा चेक कर लेंगे। देख लेंगे ना। हाँ, इधर कर दो। वायर का तो इधर चार्जर लगा दो इधर। हाँ, अच्छा सर आपका किसका अभी सर कर दो हाँ सर को देना पड़ेगा। सब सिंपल एक भी करना वहाँ करते हैं, दिखा दो ऐसे। ठीक तो हम कॉपी करवा दो। हेलो अगर वो नहीं होंगे तो चला देंगे। हाँ तो वो 24 वाले फोल्डर में देखिए। माइक अपने नंबर ऐसे आई डिफरेंस ऐसे आई नहीं बना के 30 आई करते हैं ना 30
given in the second session. There are 4 lectures. First one is Dr. C.J. Sai from National Yang Ming Chow University, Taiwan. Dr. Sai is working on the PM10 or PM2.5. He is the expert in the area of measurement of air-related particles. So I request Dr. Sai, please present your presentation. Dr. Sai, is you audible? Dr. Sai?
Yes.
Yeah. Yeah, good afternoon.
I have a little bit trouble with my power. I just found it's low in power, so I don't know whether I can.
Yeah, we can audible you.
MC down कर दो MC. Bas.
Can you move to the next? I will fix this power problem because now my laptop is low in power. I don't know. I didn't notice that until. Okay, let me try to continue. Okay, let me try to continue. Okay. Okay. Sorry. Okay. Yeah, my topic today is the field calibration and to improve the accuracy of the air sensors, including VOC and PM2.5 local sensors. And there are many co-authors of this work, and some of the results have been published in the journal. In the journal Aerosol Science, and we try to submit more papers for journal publication. So some of the results are not published yet. I hear some people's voice. Can you turn off the?
Dr. Sai, excuse me, Dr. Sai.
Yes.
Yeah.
Can you hear me?
Yeah, we can hear, but we cannot see your presentation.
It's not clear.
Presentation is not clear.
My voice is not clear.
Voice is clear, your photo is clear, but there is no presentation. Presentation.
Sorry?
What you are going to present? Slides.
Okay. Let me share my Okay, may I share my screen again? Always trouble. Okay. Let me turn it off. Let me share the screen. Share the PPT, sorry. Oh, I didn't see the PPT. Always trouble with my.
Yeah, Professor Saib, we have your recording also.
Sir, वहीं से हो.
Recording presentation. Can you run that?
We have the, so we have the recorded video.
I don't have. I don't have.
We
I sent the file to Dr. Shenka. Can you pray for me? Dr. Shenka.
Yeah, I'm here.
Kagawa.
Yeah.
Is it possible?
Yes, we can share the slides here, so you can explain them. Okay. We are uploading your slides, so you can explain them.
Okay. Maybe try my screen.
Sir, यहाँ से
have shared it.
यहाँ से कर दिया. Yes.
Now try my screen. Is that okay now?
Yes.
Okay, sorry. It's my
Please
fault.
within the 20 minutes.
Okay, I will try to finish soon because this local sensor deployed everywhere, including India, in Southeastern country, in Taiwan, around the globe. So we like to improve the accuracy of this sensor by field calibration. A lot of laboratory work, but the field calibration can take care of all the confounding factors. And of course, it's low cost. It says like in Taiwan, we spend only like a 400 per sensor box, including VOC and PM2.5. The sensor element itself is very cheap, but you have to put into a weatherproof box, including temperature, all the communication, PC board, etc., etc. And so it's largely deployed because of affordability of these sensors, and you can refine the spatial and temporal resolution for community, for industrial zone, traffic pollution, temples everywhere. And the purpose is to identify the source, to find the hotspot, and sometimes you want to do the exposure to health evaluation. And like I say, it's now widely deployed in Asia. And like in Taiwan, a colleague in Taiwan initiated this high ASAP project to work with researchers in southeastern countries to monitor the air quality by low-cost PM2.5 sensors. Of course, there are lots of publications now, even from Asian countries in terms of biomass, open burning, tailpipe emission, and cooking, and open waste burning, etc., etc. But the trouble is the accuracy is sometimes very important, especially you want to do the health-related research and also try to supplement the monitoring data. And also the calibration is important because these sensors are cheap. Sometimes the low-cost sensor has a small fan. It breaks down, and sometimes there's the soiling effect in this optics because most of the sensor is optics. This graph shows an example, the work in Indonesia, Bandung City. There are lots of roads, and traffic can go through the housing area and can pass through the traditional market or the toll gate area. So this work use Honeywell's low-cost PM2.5 sensors. And as you can see, you can find out where the hotspots are. The green means lower concentration in the morning, but even in the morning, sometimes when you pass through the traffic jam area in this region, it's become high concentration, more than 80. But in the afternoon, much less concentration. And this work is try to compute the dose versus the age, how many milligram of PM2.5 exposed per day per kilogram. The interesting finding is for children, always expose higher PM2.5 dose, and also depends a lot on the area, and also morning or in the afternoon. And also this work found there's effect on the traffic speed, because this sensor is attached on top of the vehicles. So when the traffic speed is higher and without any cover, this is the sensor inlet. Without any cover, there's the effect on wind. There's a wind has an effect on the reading. You can see lots of variations. And this is without cover, with 90-degree cover, leaving only opening at this region. Still, you have lots of variation when you run this sensor at higher speed, 50 kilometer, 40 compared to the low speed. It always has more variations. And this has a better cover, 135-degree cover the inlet, much well protected from the wind, has a lower value and less variation. So there's a lot of work on this. And this is the work in New Delhi by 22 local sensors. It's like an IoT network. And this sensor is made in St. Louis, USA. There's a small company, and you can see that this is a sensor reading PM2.5, sometimes very high, 200, 400, and also Diwali, your festival, and sometimes small event. There are several hundred microgram per cubic meter. This is, but compared to the band, because this sensor are co-located with the air quality monitor, there's a so-called federal equivalent monitor. This is more accurate, but the monitor detect a higher value, and the correlation is quite good, but the value is quite different. And this is number concentration, also show the similar trend, total particle concentration. So the message is here is if you have this kind of network, you can know when when people exposed to high concentration, and most likely in this New Delhi is in winter. But then summer is lower, and the monsoon season is also much lower. And the major finding of this work is there's a good correlation, but the accuracy is not good, especially when concentration is low, like in monsoon season. And it's pointed out this recent paper. In this recent paper, the temperature and also wind effect. This paper also identified, in fact, we found a similar wind effect also, and also similar variation and the source. And it point out the field calibration is very important because all these confounding factors. The laboratory calibration cannot use the right particle size, right particle composition for the calibration. So this is the largest sensor deployed in Taiwan, over 10,000. And we are entering the second phase. Each phase is 4 years. And the mainly deployed near the industrial park. And some are used for community, and some are used for city traffic monitors. And NYCU, my university, my department, myself is sponsored by Taiwan EPA to look at how to improve the accuracy of these sensors. And this drawing shows after calibration, our PM2.5 much agree about to the band beta gauge after calibration, only after calibration, considering all the factors, but not the wind. Wind effect, we are still looking at this effect. For the VOC, which I'm going to talk later, we just submitted and we hope we can publish it also, VOC sensors. And the most important thing we learned from the past several years, we have to collocate these chip sensors with some reference instrument at air quality monitoring stations. Otherwise, it's very hard to know the exact factors influencing the accuracy. The first one is PM2.5. It's a very famous beta gauge. It's called band 1020. There's a heater, smart heater to reduce the humidity effect, but in fact, we are still working on the trouble with this heater because sometimes it's overheating. Some of the volatile compound is heated and evaporated. And for total VOC, we use a non-Mason hydrocarbon monitor. It's a horrible instrument. It's a flame ionization detector. We have hourly methane and non-methane value at several stations. In some of the photochemical stations, we have so-called GCFID monitors. It produces hourly 54 VOC species because people also worry about the HAP, hazardous air pollutants. And in this particular work, we work on the BTAs, benzene, toluene, ethyl, benzene, and xylene. These four compounds. It's more related to industrial solvent and traffic emissions also. And this is a good example why we need to do the calibration, because we also help our government, Taiwan EPA, to do the field auditing, to look at the quality of this sensor deployed mostly on electrical posts, where we have the electrical power to power this, to get the power to this sensor box. And this is our field auditing vehicles. We have the beta gauge condition inside. It has to be conditions, otherwise it doesn't work very well. And this is near our sensors. We have this standard, but for the long years we found we must have some auditing reference, auditing standard, and we decided below 15 microgram. Taiwan is relatively clean. The allowable error is approximately 8 microgram, and greater than 15, we allow 50% error. And we also assess this auditing by optical device. This produce data every 2 minutes. It's a APM-2. It's also accurate instrument. And what we found is a lot of sensors. This is the beta gauge readings. This is APM2 reading actually. And some of the sensor produce minute data, follow very well, but some underestimate very substantially. This is on another location, similarly, a lot of underestimated, undermeasured sensors undermeasured. And a lot of location we found bias always negative, bias low compared to the reference. This is based on the beta gauge, much more accurate. So we suspect they use the station nearby to do the real-time calibration of the sensors. But these sensors are deployed near the ground. Supposedly, it should be higher than the data at the monitoring station. This is why we like to produce the after long-term calibration equation for our people to use. So first, VOC. VOC is a challenge, of course. because the biosensor is very cheap. The animal is maybe only 10 to 20 US dollars only, very, very cheap. But of course, when you put inside the box, it's different. Ambient temperature, relative humidity, and all those compounding gases all influence the sensors data. So after looking at the original data, we found we have to do something, a linear calibration or multiple linear calibration. And this multiple linear provides a better result because we take into account relative humidity, temperature, and interference gas, CO, into account. And also after some study, because we have a reference station, reference GCFID data, we convert this after calibration, the VOC data into BTEX concentrations. This is not published yet. So we look at the environmental factors, like for example, this is humidity factor, because when you have a humid air, the water molecule occupy the surface of the sensors. So the difference between the sensor and the reference FID data will change. It is a reducing concentration. So the data reduced when you have increased humidity. Conversely, when you have a higher temperature, the data is more sensitive, the sensor more sensitive and detect more VOC. That's a problem. And the confounding gas is the one we pick is the CO. When you have more CO concentration, higher CO, 200 ppb to 1600 ppb is start to increase. So we are not just talking about the small increase, several hundred ppb increase. So this graph shows without any calibration, it's overestimated 4 times, almost 4 times, 400%, and it's all positive. It's so-called mean normalized bias, 400%. And it's the same as the arrow, also 400%. It's a positive bias. So we decided we have to try this multiple linear regression. It's much better data quality. The bias become only 8% and reduce the error. This is our reading to 20 below. It's about 28%. And of course, we have to check. This is the calibration equation obtained from one station. The same equation we apply to look at the performance of sensor at different locations. This is HC, different air quality station, and look at the Tainan station. It's all give us good result, more confidence. This is all calibrated at the stations. Air quality station 15 meter high. So we encourage our local government to use this kind of calibration equation to get a more reasonable sensor readings. And if you look at just 100 ppb and greater, without calibration, lots of bias, linear calibration, reduced bias, but RMSE is still high. The multiple linear regression without CO calibration, we still have a little bit bias, -7. But after we include CO, RH, and temperature, and the concentration itself reduced to 2.6%. So it's very good performance. IMSE is still 57 because the sensor, the lowest detection limit is about 100 ppb. So below 100 ppb is very hard to use. And this is the sensor calibrated at this Zhongmin station. Sorry. And we use the same equation for the other station. We always produce similar better result. And this is time series of the calibrated low cost most sensors, all the data we compare with the reference data. It's a very good hourly comparison. And you can, with the sensor, you can also look at the minute data. But minute data, as I say, there's no reference. We only have hourly reference, no minute reference, but you can see the spike, very huge spike, it's several minutes only. So this can be a very useful tool. And for the species, this is the challenge for us also, because people like to see the health effect, the HAP, hazardous air pollutant. The sensors actually has a good correlation with some species like aromatic hydrocarbon and alkane, but some other species has a poor sensitivity. So we take this advantage, and also we make use of the photochemical station species to do the conversion. And we did the conversion, and also we try to use this information like xylene and acid-benzene ratio. When the ratio is in this region, 2.5 to 3.5, it indicates in this day traffic dominant. Also October 9th, also traffic dominant, but not on these 2 days. Most likely this is because this urban station. Most likely it's all traffic dominant, but sometimes you fall in this sort of mixed pollution range. And if you fall in this range, is industrial source range. So you can also look at the xylene-benzene ratio also. For diagnostic for source characterization, we think it can be used. And for PM 2.5 sensor, because the time limit, most of these sensors, this has been published, and they always use a small laser, and when the particle pass through this focal point, laser focal point, the scatter line is detected by the photodiode underneath the focal point. And why the wind has a strong effect on this, because this fan is always very not so powerful. And the flow rate, we try to measure it only 0.1 for particular kind of sensor. It's made in China, called Planck Tower sensors. But other sensor also similar low flow rate, Sensirion and Honeywell. And detection limit is about 10. So of course we look at the effect of this. This is like a humidity, because the humidity is a strong effect on sensor, because particle grows when your humidity reach about 70 to over 70. Then you start to grow. And then if you have low humidity.
Professor Sai?
Sorry?
Please try to summarize within 5 minutes.
Sorry, how many?
Within 5 minutes.
5 minutes. Okay, I will try to finish. So all the sensors shows when the humidity is lower, 40, 40 to 50, more agreeable to the standard. But when it become high, like 70 to 80, it start to deviate. Sensors start to overestimate. Yeah. So this is called the equation effect. Like this ammonia fluorescein, ammonia sulfate will reach about 80%, start to grow. The particle absorb water, and then because the sensor has no heater to remove the humidity, so it always overestimates. So this has to be taken into account. Again, we look at different calibration model. Of course, we want to find one that's more useful. Multiple linear and non-linear both are okay, I think. And this is before calibration, again, overestimated. And then after calibration, much better R square and much smaller bias and much smaller error. So calibration is important. Again, we calibrate one station and use the same equation for other station. And all different sensor type, you need to have different equations. This is Sensorium, the previous slides for Brand Tower and Honeywell. So I think what we learn is if the company don't pay attention, always over measure substantially for both PM2.5 and VOC. And a lot of literature and also our experience says the laboratory calibration is not enough. We need to longer term calibration to cover different seasons where you have different humidity, maybe different concentration, and maybe different composition. So you need to have a longer term, like a 1 year or 2 year calibration. And nonlinear calibration, we found for PM2.5 is good, below 30% error, useful for hard-long identification. And for the VOC sensor, we just use a multiple linear calibration. And it's good, also good for the hot long identification. But I say in the front, we have a remaining work on the wind effect. We still need to take this into account and try to cover the inlet of the sensor much better. Don't just leave it open. And we had to, again, calibrate against some good reference for the hourly concentration. I think that's all for my talk, and thank you for your attention. Thank you. I can take the question you may have. Okay, that's the end of my talk. Any question?
Accepting our invitation for making this talk. And just one question I have in your talk, that you said that the flow rate of sampler sensors are very, very low, like 0.1 or 0.5. So sometimes it's very difficult to catch all the particles. So many times when we have, especially in summertime, and in India, we have a dust particles, so it's always underestimates because of this issue. But another way, the second problem is when we have in winter very high concentration, then because when we have a very high concentration, then it is difficult to measure single particle. So again, we have a underestimation during winter when we have a very high concentration. So my understanding is so far what we did here, that we need a perfect inlet system, and in that inlet system we can incorporate this kind of sensors, so we can improve the performance of sensors. Like you said, we can prevent the wind velocity, and also the high concentration problem, and also.
Oh yeah. Okay.
So what's your comment on it?
Oh, okay. You made a good point. Because there's a term called aspiration efficiency.
Right.
In Taiwan, we found this kind of trouble. When the wind speed is strong, then it's very hard for air to suck into the sensor, especially for large particle, very hard. And at higher speed, always less concentration. In Taiwan, this is what we found. And for PM10, it's even worse. It can bias as much as 50% compared to the calm wind condition. This is the wind effect. For the concentration effect, yes, you made a good point, because the sensor normally is not calibrated for that high concentration. And it doesn't count all the particles. It just counts according to our study, unpublished, only count 1 out of 1,000 to 2,000 particles. So we compare the particle count, and we try to use the particle count and particle density convert to the mass concentration and compare to the reference. It's much lower. So we have to multiply almost 2,000 times. So this is the problem with the sensor. It doesn't have a good focus on the laser beam, and only few particles counted. So normally it's better for PM2.5, but not very good for PM10. PM10 concentration is low, and the counter, this optical counter, just use the particle number concentration to convert to the mass. But the factor you have to multiply is tremendous. It's over 1,000. So this is the current situation. Yeah. So I think like Dr. Shankar, you said the calibration is important. You need some reference, like a beta gauge, like the paper I just showed you. Professor Biswa's group, he also collocate the sensor with the air quality station. The beta gauge is used for the reference. Yeah.
Thank you very much.
Okay.
Okay, Professor. Professor, I have just one query from Dr. Nahasan from NPR. Right now we are using PM 2.5 sampler and QCM, quartz crystal micrograms, for real-time measurement. Can we compare with this results about because suppose you are going to real time? So have it sometime measure at the same time by using your technique and using QCM? Is there any comparison between QCM and this quartz crystal?
Oh, QCM. Oh, okay. QCM is widely used in India, I know. QCM for the size distribution, right? QCM count on the vibration frequency change, right? And it's more mass-based. And potentially it should be accurate if you can keep the surface from overloading, maybe. And the standard I recommend is the beta gauge, the reference. You always must have some reference. Yeah. Even you want to do you have to so-called calibrate the QCM first. Give more confidence to your QCM. QCM is real time, potentially can be used for the sensor calibration. Of course, I believe it is the case. But you have to study the QCM more. Yeah, I know there's some trouble if you overload the surface, the impaction surface. Yeah.
Thank you, Professor.
So, okay.
Thank you so much, Professor.
Thank you for your attention and your question. Thank you.
On behalf of I'm inviting Dr. Singh. Everybody knows from NPR.
Sir,
Hello. Dr. Singh was earlier chief scientist in NPM, now presently working in chief scientific officer in Field Lab. He is heading temperature and humidity metrology group in Field Lab also, as he was working in NPL also.
पीछे करो उसको बस पीछे
Well, good afternoon to all the listeners here now. I'm Dr. Y.P. Singh. Now I'm working in Fair Labs, Gurgaon. And Fair Labs is one of the very renowned laboratory in food industries, food analysis and measurements. And I was there in NPL long back after serving almost 36 years in NPL, head of temperature and humidity standards. And then in 2017, I joined Fair Labs to start with the metrology group. Because this laboratory is, as I told that it's the food laboratory, but before we heard that we have to start with the metrology. And the calibration and such kind of interaction is very, very important in the last. So in this deliberations, I'll talk about the establishment of fixed point facility for calibration of standard platinum basis thermometer. Those 5 areas thermal measurements. So I have established this facility for the primary standards in the Fair Labs. So in this deliberations, we will talk about temperature metrology, international temperature scale, new and old definition of temperature units, temperature fixed points, qualification of SPRT, standard platinum thermometer, then its calibrations, resistance, temperature relations, and calibration of SPRT at fixed points, uncertainty evaluations, which is very important, uncertainty budgets, and then how to report the results for this type of calibrations. As you know, that temperature is one of the very, very important parameter, almost utilized by each and every field. Some of the fields I have given here, you can see starting from the metrology, medical science, different thermal power plant, UV, meteorology, radiation, space, environmental, food and agriculture, oil and gas. You can be in any departments of any organization. Temperature is one of the area which is very, very important. दोबारा लगा हैंग हो गया देखना जरा अरे हैंग हो गया सिस्टम हाँ देखो जाके जरा उधर देखो जाके अच्छा क्या हुआ अरे तो मैं बोल रहा हूँ ना सेल डालो ना क्या हुआ जगन्नाथ जी
क्या वो हो रहा है अब?
Okay, yes, please. We just continue. So in this calibration, normally we have the reference documents used for the PRT calibrations. We have international temperature scale of 1990, which is the current temperature scale in practice. The supplementary information of realization of temperature fixed points, the ideal guide for realization of practice 90, and guide DKD R51 calibration of the distance. These are the the reference standards we take for this calibration of SPRTs. Environmental conditions in the laboratory is maintained as per the NABL 1 to 9. Temperature to be 25 plus minus 4 degrees and relative humidity 30 to 75%. Of course, you can maintain better than the requirement. So in temperature metrology, as you see, that it is based on the temperature fixed points from very, very low temperature, almost equivalent to absolute zero, to as high as you can measure. But in practice, the fixed point is from hydrogen focal point to copper to prelude point. And this whole scale is divided into different different points, metric points, prelude points. These standards which are defined in this. As you know that Kelvin is defined as the unit of temperature, and this was the old definition, which was in IPS 90 before 2019. That Kelvin is defined as fraction of 1/273.16 of the thermodynamic temperature of water. Now this definition remained since 1968 to 1990 because that was the best source of measurements with high accuracy with uncertainties of 3 to 10⁻⁻⁶. And full point of water is basically the temperature at which three phases altogether exist, and this is very, very high stable temperature. But it is the unit temperature depends on the properties of water, and that's why there was a need to define the unit of temperature in terms of fundamental units or in terms of independent variables. So in 2019, although what was doing since very, very long time, the new definition came to Kelvin is defined as a change of thermodynamic. That results in a change of thermal energy, KBT, because KBT is always a term which is related to thermal energy. And numerically, it is 1.386449 10⁻⁻⁰23 joules per Kelvin. So this is the way that now temperature unit is defined in terms of thermal energy, and that means 1 Kelvin or 1 degree C is equivalent to 1.38 into 10 to the power minus 23 joules of heat. And now the unit is independent of any physical property. And the uncertainty was found to be in comparison to triple point of water with 1 into 10⁻⁻⁷. And that means it is one step higher, one step better than the triple point of water. And that was the reason that since 2012 to 2019, this definition took a time to redefine the unit of temperature because of this uncertainty equivalence. So this unit can be realized in practice through Boltzmann constant, and this is, you can see, this is the device which is used nowadays to realize the unit of temperature. Now coming to the international temperature scale, which started way back 1927, but now currently the same unit is being used since 1990, 1st January 1990 for the IPS 90, and it is based on the three components. Temperature fixed points, what we call as the reliable temperature sources,
They may be equilibrium states of high purity materials. Melting point, boiling point, triple points, and freezing points where frequency basis causing reliance of the sources. But nowadays, after ITS 90, only one melting point, that is gallium melting point, and rest are either freezing points for high purity metals or triple points of high purity gases. So these were used as a temperature fixed points, then defined standards, how to measure these temperatures. We have the standard platinum resistance thermometer and photoelectric radiation thermometer. So these were the defined standards. And of course, with the mathematical relations, making the measurements in terms of the temperature with the indication of the device. So these three components then became the basis for the ITS 90, which is currently used. And these are the various fixed points you can see, starting from triple points, and the freezing points, the melting points, and the ranges are also upgraded. So the ITS 90 is starting from around 0.65 Kelvin, around minus 272 degrees to as high as the copper point, which is 1084.62 degrees Celsius. And this is still remained so far applicable currently also. And in this way, there are two different standards only. One is the standard platinum resistance thermometer as a contact thermometer, and the non-contact thermometer, which is called the spectral radiation thermometer. And the junction point to relate the temperature by contact thermometry and the non-contact thermometry is the silver freezing point. So silver point is the junction point. Below is the contact thermometry, and high is the spectral photometry. So here are the relations, how temperature is related to the different fixed points, and how temperature can be realized if you measure temperature by these SPRT. So both ranges are there. You have low for lower range from 13.88 hydrogen point to as high as the triple point. This complete the same view. And this is from the resistance ratio. W is the resistance ratio. It is the resistance at any laser temperature divided by the resistance at triple point of water. So this ratio becomes the equation which can be easily solved with the coefficient A, B, or C. These are the sum. This resistance ratio becomes the important thing for realizing the temperature in terms of the resistance of any Similarly, for higher temperature range from triple point to silver freezing point, with these 6 points, we can measure the temperature with the resistance. At clear labs, we have a triple point of water to eliminate points. These are the 6 points that have been realized in practice to get the calculation of SPRTs. So these are the 6 points we have. How to define SPRT with the SPPRT. So we have a ratio equivalent to 1.1 level, then only we got SPRT, otherwise not. So similarly for SPPRT, this can be solved. These are the 6 points we have established at the KLF. We have triple point of water, then we have melting point of gallium, steel, zinc, aluminum. Of course, boiling point by comparison method, these are CMTs, and triple point of mercury, being yet to be procured. These are the various fixed points that we have procured, and they are the specific specifications for each fixed points that we have taken. And these are the specific material property, uncertainty, the cell diameter, the cell dimensions, all these fixed points are there.
out of the various cells which are available in the international scale, we use this cell as failure. It is almost equivalent to the same type of cell that we have here also. And these are the standard classification thermometers that we secured for realization of the 6 points. And if they are, this is required that we can make it as a CRT with the different, the calibration. And so our facility either is from India or the NG lab to Crete. So we use these equipment for calibration of SPRTs. We have the SPRTs, then comparison setups, and running mechanisms. These 6 points, middling system is super small, very important light, and we use dry light for purification of water, and so civil are also there. And this is the procedure how we maintain the triple point of water. So you can see that there will be a 3 phases all together. This water inside, then ice also, and then water vapor are there. And you say the cell is used for the calculation of CRT. So how we have used the CLC 1.8 this is the specification. This is the measurement setup for triple point of water. See how that's ability is done. The visual show and the create that it can measure the seven definition of this thing. And similarly for gallium point, we have 3 point, then we have a D point, and the measurement probes for triple point of water and aluminum point. So these are the setup for complete 6 points of the range from triple point of water to aluminum point. So in the calibration procedures, we have to use the SCRT to be calibrate a triple point of water, that means from lower temperature to higher temperature, and then tin, zinc, aluminum, and then measurements are done. And these measurements, after measurements are done, then we have to evaluate the uncertainty in the measurement. You can see that there are numerous, the component of uncertainty coming. One is type A uncertainty coming from measurement data, that is repeatability, and then other 5D components coming from the various sources like reference standard, rate, unit, resolution of the unit, uncertainty due to heating effect of the sensor, immersion error, and all that these components are there. And we have to evaluate these are the formulas for type A and type B component.
ये अभिषेक जरूर पे डॉक्टर हरीश का जरा लैपटॉप कनेक्ट नहीं हो रहा थोड़ा सा वाईफाई देख लीजिए ले लो लैपटॉप.
Similarly, yes, these are the various components which have been evaluated for each point, starting from triple point to terminal point, various sources of uncertainty, and finally the measurements. And this gives you the coverage sector for evaluation of the sector. You can see that exactly at 95.45% of the confidence, for infinite degree of freedom, we have 332, which is multiplied, then we report the uncertainty in terms of expanded uncertainty. So at this point, we have to measure the corresponding values, the distance measure, and we have coverage. And also the equation, because if we use these equations in the calibration, we can also report the equation so that you can directly read in temperature, right, degree Celsius instead of reading in the distance. And these are the results of table which gives the temperature with the distance for each and every temperature point. Normally we provide for every 1 degree C, the table is provided for the complete calculation. And
There are certain remarks also given at the end. How does the SPRT is to be used during your calibration? What are the remarks? What are the precautions to be done? And how these measurements were done? If specific measurement is done when you are to report it. For example, we also reported what is the heating effect done for a particular PRT at the critical point of water. And all these measurements are done for 1 million hectares, which is very necessary, and it is done by all the bridges as in the previous talks have been done. That the bridges are so important to measure these resistances of SPR. So it is not usable to use the 6.5 digit multimeter or 8.5 digit multimeter for the calibration of SPR. So that is okay. Thank you.
One question, only one question from this side. I just would like to have a small question, sir, that you are using the SPRT as a reference standard for the calibration. But what about the fixed points? Should we calibrate it, or are you doing some stability or what? Because that component, I'm not getting that component in the uncertainty calculation about the fixed points. That's my question. Thank you.
It is coming. Let's see that if you see here, repeatability is the measurement data. The reference standard is a fixed point. So each fixed point is calibrated where from we have reviewed it is from fluid, so they have given the least data, and you can see 0.5. All values are in millikelvin, so millidegree C. So 0.05 millidegree C. These are the values which are coming from the reference standard, that means the fixed point. For PRT, another, the PRT, because PRT is used as a standard for measurement. So we also use what is the uncertainty of the SPRT we are using. So that's the okay. If no questions, thank you so much.
Thank you, Dr. Next. In continuation of this, now we are